There was no falling sensation. That is the first thing that will confuse you. Your inner ear has nothing to report, no rushing air, no ground getting closer, so your brain quietly decides that you are standing still. You are not standing still. You are moving at roughly 800,000 kilometers per hour, and there is nothing within 4 light years to measure that against. And the air in your lungs is already leaving. It leaves whether you want it to or not. This is the part people get wrong. You cannot hold your breath out here the way you hold it underwater because the pressure gradient is running the other direction. Roughly 1 atmosphere inside your chest, effectively 0 outside it. Your lungs empty themselves through your open mouth in a couple of seconds. And if you clamp down and try to keep that air, you tear the tissue. The vacuum does not negotiate. So forget what you saw in the films. You do not swell up and burst. You do not freeze into a statue in a shower of glittering ice. Your eyeballs stay where they are. Blood does not spray from your ears. Human skin is a remarkably good pressure vessel, tough and elastic. It will hold you together far longer than the plot of any movie ever allowed. What actually happens is slower and quieter and considerably more intimate. We know this with unusual precision, and we know it because of one very bad afternoon in Houston. December 14th, 1966. Inside the Manned Spacecraft Center, there was a chamber called the Space Environment Simulation Laboratory, a steel room the size of a small house that could be pumped down to something close to the pressure of orbit. NASA used it to test suits with actual human beings inside them, which was, at the time, considered reasonable. The man inside the suit that day was a technician named Jim LeBlanc, 20-something, competent, doing a run that had been done before. The chamber was at an altitude equivalent of about 150,000 feet, which for practical purposes is space. He was tethered to the outside world by hoses. One of them carried the pressurized air that was keeping his suit inflated and keeping him alive. That hose came loose. The suit went from 3.8 pounds per square inch to under 1/10 of that in something like 10 seconds. LeBlanc heard the air go. He said later that he could feel the suit collapsing around him, going soft, losing its shape the way a balloon does. And then he felt the strangest sensation any human being has ever accurately reported and lived to describe. He felt the saliva on his tongue begin to boil. That is not poetry. At low enough pressure, water boils at body temperature. Not because it is hot, because there is no longer enough weight of atmosphere sitting on top of it to keep it liquid. The wet surfaces of you, tongue, eyes, the lining of your mouth, all of it starts turning to vapor at 37 degrees Celsius. The moisture leaves your body in a soft, invisible hiss. You will not hear it. There is nothing to carry the sound. LeBlanc got about 14 seconds. That is how long he stayed conscious, and we know the number because there were people watching him through the glass with stopwatches and a camera running. He remembers the boiling. He remembers going down. Then a chamber operator named Dick Williams started an emergency repressurization. An engineer went in through the airlock while the pressure was still climbing, and Jim LeBlanc woke up on the floor of a steel room, alive, with an earache. He walked out, went back to work, lived for decades afterward. The whole thing lasted less than 90 seconds from failure to rescue. And that 90-second window is the only reason we have a first-hand account of vacuum exposure instead of a coroner's report. It also gives us the number that matters most to you, right now, floating where you are. Somewhere between 9 and 15 seconds of useful consciousness. That is the budget. That is all of it. Here is what fills those 15 seconds. The swelling starts almost immediately, and it has a clinical name: ebulism. Water vapor forming in your soft tissue, under your skin, in the loose spaces around your joints and your face. You puff up, roughly to twice your normal volume in the worst affected places. It is grotesque, and it is survivable because that tough, elastic skin holds the pressure in. You become, briefly, a swollen version of yourself. There's a line in the sky where this becomes possible, and it sits at about 19 kilometers up. Aviators call it the Armstrong limit, after Harry Armstrong, an American flight surgeon who worked out in the 1940s that above that altitude, the pressure drops below 63 millibars and body temperature water simply cannot stay liquid. Every commercial flight you have ever taken has cruised at roughly half that altitude. The line is closer to the ground than most people would like to know. Your blood, meanwhile, does something worth understanding. It does not boil in your veins, not while your circulatory system is intact, because your vessels and your heart maintain their own pressure independent of the outside world. Your arteries are holding the line. What is failing is the exchange. Your lungs are now a pair of empty bags, open to nothing, and the blood arriving there is not being loaded with oxygen. It is being stripped of the oxygen it already had. That detail is genuinely nasty. In a vacuum, the partial pressure of oxygen outside your body is zero, so the gradient reverses. Your alveoli begin pulling oxygen out of your bloodstream and venting it to space. You are not merely failing to breathe in. You're being actively unbreathed. Deoxygenated blood leaves your lungs, reaches your brain about 9 seconds later, and that is the moment the 15 seconds ends. Before then, though, you are awake. Fully, unpleasantly awake. Vision goes first at the edges of a gray, narrowing tunnel, because the retina is one of the most oxygen-hungry pieces of tissue in the body, and it starts complaining immediately. Hearing goes almost at once, though that is academic out here. Your ears may hurt as the eardrums bulge outward, and, if you're unlucky, rupture. LeBlanc's earache came from exactly that. The cold, which is the thing everyone expects, does not arrive. Not yet. There's no wind chill because there's no wind. The exposed wet surfaces of your eyes and mouth will feel a sharp chill from evaporation. The same trick that makes rubbing alcohol feel cold on skin, and that is it. Your core temperature at the 15-second mark is still essentially normal. You will die warm. That surprises people more than anything else in this chapter. So run the clock honestly. Second 1. The air leaves you in a rush you can feel in your throat. Second 3. Your suit or your chest is empty and your tongue has started to fizz. Second 6. The tunnel is closing in from the sides and your skin is tightening as it swells. Second 9. The first badly oxygenated blood reaches your cortex. Second 12. You are gone. Second 15. Generous. And then there's a mercy in it of a kind. Unconsciousness in vacuum is fast and it is total. No struggle, no thrashing, no long suffocating panic like drowning. The lights simply go off. Air Force research through the 1950s and 60s, much of it on dogs and chimpanzees at Brooks Air Force Base in Texas, found that animals could be exposed for up to about 2 minutes and still be revived with no permanent damage. Past that, nothing came back. Which means there's a rescue window, and it is roughly 90 seconds wide. That number has quietly shaped every airlock, every hatch, every emergency procedure ever written for human spaceflight. 90 seconds to get pressure back around a body. It is the reason for the drills, the reason for the buddy checks, the reason a suit has redundant hoses at all. Somebody sat down decades ago and did this arithmetic so that nobody would have to do it in real time. Nobody is going to do it for you. That is the whole premise of where you are. There is no chamber operator with a hand on the repressurization valve, no engineer coming through the airlock, no glass with faces behind it. The nearest human being is somewhere behind you, at a distance that light itself takes years to cover. Your 90-second window opened the moment you arrived, and it is already most of the way closed. I keep coming back to LeBlanc's detail about the saliva, and I think I know why. Every other symptom on the list is something happening to a body. That one is something happening to a person. He was standing there, thinking, aware, and he noticed the taste of his own mouth changing state. Then he had about 12 seconds left to think about it. Of all the ways the universe could have announced itself, it chose the inside of a man's mouth. You get those seconds too. 15 of them, more or less fully conscious in the emptiest environment the universe offers. And the strange thing is that they are usable. You can look. You can turn your head. Physics gives you a short, brutal window of clear perception in a place no living thing has any business perceiving, and then it closes the window and moves on. So spend them well. Look up. Above you, in every direction that the word above stops meaning anything, there are stars. Not the smeared, trembling stars you know from a summer field on Earth, softened by 12 kilometers of moving air. These are hard, fixed, absolutely still, like something printed rather than something burning. Nothing twinkles out here because twinkling is an atmospheric effect, and you have left the atmosphere so far behind that it is no longer even a memory of a place. And it is silent, not quiet, silent in a way that has no equivalent on Earth. And we will spend a whole chapter on what that silence eventually does to a mind. For now, just register the fact of it. There is no sound in this place, no ambient hum, no ringing, nothing arriving at your ears from outside your own skull. Because sound is a pressure wave in matter, and there's effectively no matter here to wave. Effectively. That word is doing a lot of work, and I want to flag it now because it becomes important later. Interstellar space is not truly empty. It is the best vacuum you will ever encounter, better than anything humans can manufacture on Earth, and it still has things in it. Atoms, fields, radiation, objects. The emptiness is a very good approximation rather than a fact, and the difference between those two ideas will eventually kill you in ways vacuum never could. But that is later. Right now, you are a warm, swelling, unconscious human body with clean, hard starlight falling on your skin and nothing to interrupt it. Your heart is still beating. It will keep going for a few minutes yet, out of habit, pushing oxygen-starved blood around a system that has no way left to refill it. You are technically still alive. The universe has not finished with you. It has barely begun. Because the story people always tell about this place is a story about cold. Frozen bodies, ice crystals, the black, airless deep freeze. It is the first thing anyone thinks of, and it is almost entirely wrong. And the reason it is wrong tells you something genuinely disturbing about where you have ended up. The cold out here is real. It is 2.7 degrees above absolute zero, and it cannot touch you. 2.725 degrees above absolute zero. That is the temperature of the place you are in, measured to 4 significant figures, and it is the same number in every direction you could possibly point. There is no colder natural environment anywhere, and it is going to take that cold somewhere between several minutes and several hours to make you meaningfully uncomfortable, which is a sentence that should not make sense and does. The reason is simple once you say it out loud. Cold is not a substance. It does not travel, and it does not arrive. What actually happens when you feel cold is that heat leaves you, and heat needs a way out. There are exactly 3 ways out in this universe: conduction, convection, radiation. Out here, 2 of them have been switched off. Conduction needs contact, molecules of something touching molecules of you, taking your energy and passing it along, the way a metal railing in January steals the warmth from your palm in under a second. There is nothing here to touch you. Convection needs a fluid that can carry heat away in bulk, air moving across your skin, water pulling warmth off your body 25 times faster than air can. There is no fluid. There is no air. There is no wind chill in a place with no wind. So you're left with radiation, and radiation is slow. Every warm object throws energy out as infrared light, all the time, whether or not there's anything around to receive it. You're doing it right now. Roughly 900 watts of it, if you run the Stefan Boltzmann numbers on about 1.5 square meters of skin at 33 degrees Celsius. 900 watts sound violent. Is the entire budget. On Earth, that number does not matter, because everything around you is also radiating, and you absorb almost as much as you emit. Walls, furniture, other people, the ground. Your net loss on a mild day is closer to 100 watts. Out here, nothing sends anything back. The sky you are radiating into is at 2.7 degrees, so it returns effectively nothing. And for the first time in your life, your heat is going out one way with no return traffic at all. Do the arithmetic anyway. A 70-kilogram human body holds roughly 240,000 joules of heat for every degree Celsius. Losing 900 joules a second, you would drop a full degree in about 4.5 minutes. 9 degrees, which is deep and lethal hypothermia, in something like 40 minutes. That is the naive version, and the real body is slower and stranger than that. Because the heat has to get from your core to your surface before it can leave, and your body is genuinely good at refusing to let that happen. Blood vessels near the skin clamp shut within seconds of a cold signal. Your outer layer becomes insulation, so your fingers and your face chill fast within minutes, while the deep organs stay stubbornly warm for hours, hoarding what they have like a household rationing firewood. The dying happens from the outside in. None of which is going to be your problem, because you have already been unconscious since second 12, and your heart will stop long before your core temperature does anything interesting. This is the part one find genuinely hard to sit with. The most famously cold environment in existence is not what kills you in it. You suffocate in a warm body under a sky that is 3 degrees above the coldest temperature physics permits. We know this from the only 3 human beings who have ever actually died in space, and their names deserve to be said. Georgy Dobrovolsky, Vladislav Volkov, Viktor Pochayev. Soyuz 11, June 30th, 1971, returning from 23 days aboard the world's first space station. At 168 kilometers of altitude, a pressure equalization valve jolted open during module separation. The cabin emptied in under a minute. They were not wearing pressure suits, because the Soyuz cabin of that era was too cramped for 3 men in suits, and somebody had decided that was an acceptable trade. Telemetry shows Patsayev's heart rate spiking, then flatlining. All 3 were dead within about 2 minutes, while the capsule flew a perfect automated re-entry and landed softly on the steppe of Kazakhstan. The recovery team opened the hatch expecting 3 living men. What they found were 3 seated bodies still warm to the touch, with dark blotches on their faces and blood in their ears and nostrils. Warm. That is the detail that ends the argument about the cold. They had been exposed to genuine vacuum. They had died from it, and the coldest environment in the universe had not managed to lower their body temperature in any way a human hand could detect. If you want the inverse of the myth, look at how spacecraft are actually built. The persistent engineering nightmare of human spaceflight is not staying warm. It is getting rid of heat. Bodies produce it, electronics produce it, sunlight adds more, and none of it can be fanned away because there's nothing to fan. The International Space Station carries enormous white radiator panels for exactly one purpose: to dump waste heat into the dark before the crew cooks. Inside a spacesuit, the same problem gets personal. Under the outer layers, an astronaut wears a garment threaded with about 90 meters of narrow plastic tubing, circulating chilled water across the whole body. Apollo crews carried water sublimators that vented ice into vacuum to shed heat. Every one of those systems exists because a human being sealed in a bag in space will overheat first, and the vacuum will politely decline to help. There is an object in most kitchens that works on this exact principle. It was invented by a Scottish chemist named James Dewar in 1892. A thermos flask, 2 walls with the air pumped out from between them, so conduction and convection have nowhere to happen, leaving only slow radiation across a silver gap. Coffee stays hot for hours. You're floating inside the largest vacuum flask in existence, and you are the coffee. So where does 2.7 degrees actually come from? If nothing out here is generating heat, it comes from an event, and the event is the beginning of everything. The whole universe is soaked in a faint microwave glow, released about 380,000 years after the Big Bang, when the cosmos finally cooled enough for light to travel freely. That light has been stretching and cooling ever since. It is the oldest thing you will ever be able to detect. 2 men found it by accident: Arno Penzias and Robert Wilson, 1964, working at Bell Labs in Homedale, New Jersey, on a large horn-shaped antenna designed for satellite work. They had a persistent hiss in their data that would not go away. They pointed the horn in different directions. Same hiss. They checked the wiring, the amplifiers, the receiver, everything, and the noise stayed exactly where it was. They found pigeons nesting in the antenna. They evicted the pigeons, scrubbed out what Pentheus delicately called white dielectric material, and the hiss remained. It took a phone call to Princeton before anyone realized what they were listening to. They had cleaned bird droppings out of a horn while trying to eliminate the afterglow of the birth of the universe. They got a Nobel Prize in 1978. That glow is the thermal floor of reality, and it is falling. In the early universe, this same radiation was thousands of degrees, hot enough to fill all of space with light. Roughly 13 billion years of expansion have stretched it down to 2.725 Kelvin, and it will keep dropping forever. The cold you are floating in is not a permanent feature. It is a temperature on its way down, and you happen to be reading the gauge early. Now something genuinely odd. Your body will not decay, not in the way bodies do. Decomposition is a biological process carried out by bacteria and fungi and the enzymes in your own gut, and every one of those organisms needs moisture and warmth, and in most cases oxygen. Out here, the water leaves within days, sublimating straight from ice to vapor without ever being liquid. The bacteria die with the rest of you. What you become is a mummy, a freeze-dried one, hard and light, with your features more or less intact because there is nothing present to disassemble them. No air to oxidize you, no insects, no scavengers, no weather. On Earth, even glacier bodies eventually distort under ice pressure, and Otzi in the Alps was found flattened and battered after 5,000 years. You would be flatter than nothing at all, and you would keep your face. For how long is a question with an uncomfortable answer? Millions of years at minimum. The only real erosion mechanisms out here are radiation slowly breaking chemical bonds and the occasional micrometeoroid, and both work on timescales that make geology look impatient. The sun will have consumed the Earth before anything meaningful happens to a body drifting between the stars. You will outlast the planet you were made on. I think that is the actual horror of this chapter, and it took me a while to see it. Fire consumes. Water dissolves. Earth breaks things down and hands the pieces back. Every environment we come from is in the business of recycling, and we build our entire emotional relationship with death around that assumption. The vacuum has no such business. It does not take you. It simply keeps you exactly as you were indefinitely. There's a version of this that already exists in a small way. On the moon, in the Sea of Tranquility, there's a boot print pressed in a dry regolith in July 1969. No wind has touched it. No rain. It is still there, sharp at the edges, and it will still be recognizable in a million years. That is what preservation looks like in an environment with nothing in it. Now scale it up to a body in interstellar space. And you will be moving the whole time, not toward anything. Your velocity is inherited whatever you had when you arrived, and with nothing to slow you down, you keep it exactly. No friction, no drag, no air resistance. Newton's first law stops being an idealization out here and becomes the plain literal truth about your afternoon. A body in motion, in a place designed to never interfere. Almost never interfere, because when I said there's nothing out here to conduct heat away from your skin, I was rounding. Space is the best vacuum you will ever meet, and it is not a perfect one, and the difference is measurable. There are atoms in this room, not many, enough to be counted, enough to be tasted by the right instrument, and enough, given a few million years, to matter. In 2012, a machine built in the 1970s crossed into this same emptiness and began sending home numbers about it. Very small numbers on a very weak radio signal from a transmitter with less power than a refrigerator bulb. And what those numbers described was not nothing. It was a thin, hot, invisible sea blowing steadily past a spacecraft at 90,000 kilometers an hour. Hold out your hand. Somewhere in the volume of space your palm just swept through, there's one hydrogen atom, possibly two. That is the density of the place you are floating in, roughly 1/10 of an atom per cubic centimeter. And it is the emptiest substance in the known universe. It is also unambiguously a substance. Space is not a void with things in it. Space is a very thin thing. Get a sense of the ratio, because the ratio is the story. The air in front of your face at sea level holds about 25 billion molecules in every cubic centimeter. Out here, that number falls to 1, or to a fraction of 1. That is a dilution factor of around 100 billion. If you shrank a room of ordinary air until it held 1 atom per cubic centimeter, that room would be wider than the solar system. Humans cannot make anything this empty. We try very hard. The beam pipes of the Large Hadron Collider are pumped down to one of the most extreme vacuums achievable on the planet, and they still contain something like 100,000 molecules per cubic centimeter. The best ultra-high vacuum laboratories in the world manage a few hundred. Interstellar space beats every one of them by orders of magnitude, effortlessly, everywhere for free. What is in it mostly is hydrogen, 9 atoms out of every 10. Helium takes almost all the rest, and then a smear of everything else the galaxy has manufactured in the cores of dead stars. Carbon, oxygen, nitrogen, silicon, iron, all of it at trace concentrations. There's roughly 1% dust by mass. Those numbers are the entire material inventory of the space between the stars, and every atom in your body was drawn from a version of it. Now the part that breaks people's intuition. The gas immediately around you is hot. Not cool, not tepid. In the warm, ionized regions of the local interstellar medium, the temperature runs to something like 8,000 Kelvin, which is hotter than the visible surface of the sun. You're drifting through a plasma that would vaporize steel, and it will do absolutely nothing to you. Temperature, it turns out, is a measure of how fast individual particles are moving. It says nothing about how many there are. 8,000 Kelvin means the atoms out here are traveling at roughly 15 kilometers per second, which is genuinely fast. It also means you get hit by a handful of them per second, and each one carries less energy than a mote of dust. Heat needs volume to be dangerous, and this gas has none. Let me make it concrete. Sweeping through this medium at 17 kilometers per second, a human body with about 1.5 square meters of frontal area intercepts something on the order of 3 billion hydrogen atoms every second. Sounds like a hailstorm. Weigh it. Those 3 billion atoms come to about 5 billionths of a billionth of a kilogram. Drift for 1,000,000 years, and you will have collected a fraction of a gram of galaxy. Everything we know about this stuff at first hand comes from 2 spacecraft launched in 1977, and they were never designed for the job. Voyager 1 and Voyager 2 were built to photograph Jupiter and Saturn. They carried instruments intended for planetary magnetospheres. Then they kept going decade after decade, and the mission quietly turned into the only direct survey of interstellar space that will exist in our lifetimes. There's a cruel irony in Voyager 1's toolkit. Its plasma science instrument, the one built specifically to measure the density of the medium it was flying through, broke in 1980, dead for 32 years before it reached the thing it was made to study. So the team had to measure a plasma without a plasma detector, using an instrument designed to listen to radio waves. The trick belongs to Don Gurnett and his group at the University of Iowa. Plasma rings. Give it a shove from a solar flare, for example, and the electrons in it oscillate at a frequency that depends on exactly one thing: how many electrons there are per unit volume. Measure the pitch, and you have a density. The plasma wave subsystem on Voyager 1 could hear that pitch. Iowa had been waiting since 1977 to use it this way. In late 2012, the pitch shifted, and it shifted hard. The electron density around the spacecraft jumped roughly 40-fold to about 0.08 per cubic centimeter. The date the team eventually settled on for the crossing was August 25th, 2012. It took them until September 2013 to be confident enough to announce it. because nobody wanted to be the person who declared humanity had left the solar system and then had to walk it back. They turned the data into audio, and you can listen to it. It is a rising whistle, thin and eerie, more like a wet finger on glass than anything mechanical. It is not sound in any real sense, since there is no medium out there to carry sound to a human ear. It is an electric field oscillation translated into a frequency our hearing can reach. Even so, it is the closest thing that exists to a recording of the noise between the stars. Voyager 2 got the better instrument. Its plasma detector survived, so when it crossed on November 5th, 2018, it made the direct measurement its twin never could. It found the medium colder and denser than models had predicted, with a thin transitional layer at the boundary that nobody had seen coming. 2 spacecraft, 6 years apart, at different points on the boundary, and the boundary was a different shape in each place. Then there's the dust, and the dust is the part that could actually hurt. About 1% of the mass out here is solid grains, mostly silicates and carbon, typically around 1/10 of a micrometer across. Smaller than a bacterium, individually harmless. There are enough of them spread across enough light years to dim and redden every distant star you look at, which is why astronomers have to correct for something called interstellar extinction before any measurement means anything. We have some of these grains in a laboratory. The Stardust mission, launched in 1999, flew a collector made of aerogel through space for years and returned the capsule to the Utah desert in January 2006. Buried in that aerogel, among thousands of cometary particles, researchers eventually identified a handful of candidate interstellar grains. 7 of them, 7 specks of the galaxy, sitting in a clean room in California. Now change one variable and watch this harmless sea turn lethal. Speed. At 17 kilometers per second, the medium is nothing. At half the speed of light, those same hydrogen atoms arrive with the energy of a particle accelerator beam, and 1/10 of an atom per cubic centimeter becomes a wall of hard radiation that would strip a spacecraft's hull and everything behind it. The emptiness is only harmless because you are slow. This is the quiet reason interstellar travel is harder than the distance suggests. Every serious study of a fast starship runs into the same problem. The destination is not the difficulty, and neither really is the fuel. It is that the void becomes abrasive at speed. Push a vehicle to relativistic velocity, and the galaxy starts sandblasting it with individual protons, billions per second, each one arriving like a bullet made of light. The medium also has structure, which surprised astronomers when they worked it out. It is not one uniform fog. It comes in phases like water does. Cold neutral clouds at 50 Kelvin, warm neutral gas at 8,000, warm ionized regions, hot ionized bubbles at 1,000,000 degrees, blown open by supernovae, so tenuous they hold almost no matter at all. Dense molecular clouds where the temperature falls to 10 Kelvin and chemistry begins. Those molecular clouds are where it gets strange. Radio astronomers have identified something like 270 distinct molecules floating in interstellar space, and the list stopped being boring a long time ago. Water, ammonia, formaldehyde, methanol in quantities that defy description, long carbon chains, sugars. In 2009, a team looking at Sagittarius B2 near the galactic center reported ethyl formate, which is the compound that makes raspberries taste like raspberries. So the galactic center may, in a limited chemical sense, smell faintly of fruit. I enjoy that fact more than I should. It also contains propyl cyanide, which is closer to nerve agent than dessert, and vast reservoirs of alcohol that no one will ever drink because the density is a fraction of an atom per cubic centimeter. The universe stocks the ingredients of biology at concentrations that make biology essentially impossible. Astronauts who come back inside after a spacewalk do report a smell, incidentally. Burnt metal, seared steak, spent gunpowder. Several of them independently described it the same way. And the leading explanation involves single oxygen atoms clinging to their suits and recombining once they reach cabin pressure. That is low orbit chemistry, hundreds of kilometers up. Out here, there's nothing to cling and nothing to recombine, and no nose that still works. The atoms passing through your body right now were made somewhere, and the somewhere matters. Hydrogen is original equipment, forged in the first minutes of a universe. Everything heavier was assembled inside stars and then thrown back out, either in slow stellar winds or in the detonation of something enormous. The medium you are drifting through is exhaust, ash from dead suns, thinned across light years, waiting to be gathered up again. And it will be gathered up. That is the loop. Molecular clouds collapse under their own weight, ignite new stars, and those stars build new elements and eventually return them. The sun was assembled out of exactly this material about 4.5 billion years ago, along with the Earth, along with the calcium in your teeth. You are floating in the raw stock. You are also, structurally, a sample of it that briefly learned to have opinions. Which is a nice thought, and I want to sit in it for a second before ruining it, because this thin sea has a boundary, and the boundary is the actual subject of the next hour. For your entire life on Earth, not one atom of true interstellar medium ever touched you. Not one. Something has been standing between your species and this gas since before your species existed. It is a bubble, and the sun blows it. A steady outward gale of charged particles that pushes the galaxy back to a distance of roughly 18 billion kilometers in every direction and holds a cavity open inside the interstellar medium. Everything humans have ever done happened inside that cavity. Every planet, every probe, every photograph, all of it under the same invisible awning. You're not under it anymore. There is a threshold somewhere behind you, a shifting membrane where the sun's grip finally lost to the pressure of the galaxy, and you crossed it without any sensation at all. No yod, no va onde marquer. 2 spacecraft have made that crossing, and each of them found something different waiting on the far side, and one of them found something nobody had modeled at all. The sun is leaking. It has been leaking for 4.5 billion years, and it will keep leaking until it dies. Every second, something like 1 million tons of its outer atmosphere tears free and flies outward at between 400 and 800 kilometers a second. We call it the solar wind, which makes it sound gentle, and it is the single loudest thing your star does. That wind does one enormously important thing. It pushes. It blows outward in every direction at once, and it keeps blowing until it runs into the pressure of the interstellar medium coming the other way, and where those 2 pressures balance, it stops. The result is a cavity, a bubble of solar material carved into the galaxy, roughly 18 billion kilometers in radius, with all 9 planets and every human artifact ever launched sitting inside it. You have spent your entire existence inside that bubble, and so has every living thing you have ever heard of. Life on Earth has never once experienced the raw, interstellar environment. There has always been 120 astronomical units of solar wind standing between the biosphere and the galaxy, absorbing incoming radiation, deflecting charged particles, holding the line. It is the largest structure the sun makes, and almost nobody thinks about it. 2 objects have ever left it. Both were launched in 1977 by a country that had just come out of Vietnam. Both were built with technology cruder than a modern car key, and both are still transmitting. Voyager 1 and Voyager 2. Between them, they have made every measurement humanity possesses of what the edge of the sun's influence actually looks like, and it looks nothing like the neat diagram in the textbook. The first boundary they hit was not the edge. It was a shock front, out at somewhere between 80 and 100 astronomical units. The solar wind slams into the accumulated pressure ahead of it and abruptly slows from supersonic to subsonic, the way water piles up in a ring around a tap hitting the bottom of a sink. Astronomers call it the termination shock, and Voyager 1 crossed it in December 2004 at 94 astronomical units. Voyager 2 reached it in 2007 at 84 astronomical units. 10 units closer, and then its twin. That difference mattered enormously because it proved the bubble is dented, lopsided, not a sphere at all. And Voyager 2 did something even better. It crossed the shock 5 separate times over the course of a few days because the boundary itself was moving, sloshing back and forth over the spacecraft like surf over a stone. Past the shock is a region called the heliosheath, and it is the strangest place either spacecraft has been. The solar wind here is hot, slow, turbulent, piling up against the galaxy. Around 2011, a team, led by Marav Ofer, reported that the magnetic field in there appears to break apart into a froth of self-contained magnetic bubbles, each perhaps 100 million miles across. A foam. The outer wall of the solar system is a foam. Then, on August 25, 2012, at 121 astronomical units from home, Voyager 1's instruments recorded something abrupt. The count of solar particles around it collapsed by a factor of about 1,000 in the space of a few days. Simultaneously, the galactic cosmic ray count jumped roughly 9% and stayed up. The sun stopped and the galaxy started, and the transition took less than a week. That is the heliopause. That is the edge. Not a wall in any solid sense, no membrane, nothing a hand would feel, simply the surface where the sun's outward pressure finally loses to the pressure of the interstellar medium pushing back. Somewhere behind you, you passed through it. There was no marker. There was no sensation. Your star's jurisdiction ended, and you did not notice. Voyager 2 followed on November 5th, 2018, at 119 astronomical units, and because its plasma instrument still worked, it saw details its twin had missed. A thin transitional layer at the boundary that no model had included. Interstellar gas leaking inward through the interface. Solar material leaking outward. The two are not cleanly separated. They interpenetrate over billions of kilometers, and the line between inside and outside is a smear. The shape of the whole structure is still argued about. For decades, everyone assumed a comet, with a long streaming tail behind the direction of the sun's travel. Some models now propose a two-lobed object closer to a crescent or a croissant with no real tail at all. The observations are compatible with several shapes, and nobody has resolved it, which is an unusual thing to be able to say about the object we all live inside. One spacecraft was built to map it from the inside. The Interstellar Boundary Explorer launched in October 2008, a small satellite in Earth orbit that detects energetic neutral atoms coming back inward from the boundary and builds a picture of the edge without going anywhere near it. In 2009, it delivered its first all-sky map, and the map had something on it nobody had predicted. A ribbon, a bright, narrow band of particle emission stretching across the sky in a great arc, 2 to 3 times brighter than everything around it. No model had it. 14 competing explanations appeared within a year, most involving the galactic magnetic field draping across the outside of the bubble. The leading candidates are plausible, and none of them is settled. There's a stripe painted on the wall of the solar system, and we do not fully know why. Ibex also killed a piece of textbook physics. Every diagram used to show about shock ahead of the heliosphere, a sonic wave front like the one in front of a supersonic jet. Then Ibex measured the sun's speed through the local medium at roughly 23 kilometers per second, meaningfully slower than the older estimate, and slow enough that a true shock probably never forms. What is out in front is gentler, a bow wave, water heaping up ahead of a slow boat. Understand what that bubble was doing for you, though. It blocked something like 3/4 of the galactic cosmic radiation that would otherwise reach the inner solar system. When the sun is active, the wind blows harder and the shielding improves. When the sun goes quiet, the bubble contracts and more gets through, and you can see in the data as an 11-year rhythm in radiation levels at Earth. Your star was standing in front of you. It is not standing in front of you now. Outside the heliopause, the galactic cosmic ray flux is roughly 4 times what it is at Earth's orbit, arriving from every direction with no preference and no shelter, and there is no 11-year cycle to wait out. This is the ambient condition of interstellar space. We will spend 2 entire chapters on what it does to the inside of a human body, because it deserves them. The Voyagers are dying out there, slowly, in a way that is genuinely difficult to read about. Each one runs on the heat of decaying plutonium-238, converted directly to electricity. That heat source loses about 4 watts of usable power every year, and it has been losing it since 1977. There is no fixing that. The half-life is the half-life. So the engineers at the Jet Propulsion Laboratory have spent decades performing a slow triage. Cameras off in 1990, heaters off, one by one, on instruments the manual swore would fail below their rated temperature, and which then kept working anyway at temperatures nobody had tested. Whole subsystems retired to buy a few more years for the particle detectors. They're turning off the lights in a house, room by room, from 400 billion kilometers away. The radio link is the part that stops me cold. Voyager 1 transmits on about 22 watts, roughly a domestic light bulb. By the time that signal reaches Earth, spread across billions of kilometers, the power arriving at a 70-meter dish is around 1/10 of a billionth of a billionth of a watt. We hold a conversation with an object outside the solar system using less energy than a firefly, and the round trip takes about a day and a half. They're not the only ones out there. Pioneer 10 crossed into the outer solar system decades earlier and sent its last faint signal in January 2003. Pioneer 11 went silent in 1995. Both are still flying, mute, in roughly the direction they were pointed. New Horizons, which photographed Pluto in 2015, is still awake and still reporting, and will run out of plutonium long before it reaches the boundary. Add them up, and the total is 5 machines. 5 objects out of everything our species has ever built on trajectories that leave the solar system, against roughly 8 billion of us and about 100,000 years of human history. That is the size of our footprint outside the bubble. And one of those 5 is the reason we know anything at all about where you are floating. Voyager 1 is currently around 170 astronomical units out, 25 billion kilometers. It covers another 3.5 astronomical units every year, and it will keep doing that essentially forever, long after the last transmitter dies sometime in the next decade or so. After that, it becomes what you are, an unpowered object in free fall between stars, carrying no signal, going somewhere will not arrive for tens of thousands of years. The heliopause is not fixed, by the way, which is worth knowing if you're trying to work out where you stand. It breathes. It expands and contracts with the solar cycle, moving in and out by astronomical units over the course of years, and both Voyagers have detected it wobbling past them. The edge of the solar system is a tide. Whatever line you crossed has since moved. That is the last piece of the sun you will get. Everything from here on belongs to the galaxy, and the galaxy keeps different records. The particles are hotter and stranger. The magnetic fields belong to something 26,000 light years across, and the nearest object with a name is 4.25 light years away and has nothing to do with you. And this region has a history you should probably know about because it explains why it is so quiet here. Instruments have mapped the density of interstellar gas around the sun out to hundreds of light years, and the map shows a hole. An enormous, low-density cavity several hundred light years across, with the sun sitting near the middle of it almost entirely by coincidence. Holes like that do not form on their own. Something has to push the gas out, and there is only one process in the galaxy with enough force to clear a volume that size. In 2022, a team working with data from the Gaia mission reconstructed the sequence, and the sequence turned out to be a chain of detonations that began around 14 million years ago and did not stop for a very long time. There's a hole in the galaxy, and you're inside it. Not a metaphorical hole. A measured cavity in the interstellar gas, roughly 300 light years from one wall to the other, where the density falls to about 1/20th of the galactic average. Astronomers named it the local bubble, which is the blandest possible label for the aftermath of a massacre. It was first suspected in the 1970s when X-ray detectors kept finding a soft glow coming from every direction at once. The only good explanation was a large volume of very hot, very thin gas surrounding the solar system. At something like 1,000,000 degrees, so tenuous it holds almost no heat at all. Then came the radio surveys, then the ultraviolet absorption studies, and slowly the shape of the hole came into focus. Getting the shape right required knowing where things are in 3 dimensions, and until recently we simply did not. Then the European Space Agency flew Gaia, launched in 2013, which measured the positions and distances of nearly 2 billion stars with absurd precision. Give astronomers accurate distances, and everything changes. Suddenly, the local gas could be mapped as a solid object rather than guessed at from shadows. In January 2022, a team led by Catherine Zucker published the reconstruction in Nature, and it read like a forensic report. The bubble was blown open by a chain of supernovae, at least 15 of them. The sequence began roughly 14 million years ago and continued, one massive star at a time, each detonation adding its shove to the expanding shell of gas. The killers have an address. Most of them came from the Scorpius and Taurus Association, a loose cluster of young, massive stars a few hundred light years away, the kind of stars that burn through their fuel in 10 million years and then collapse. Groups like that go off in sequence, like a string of firecrackers laid across the sky, and this one happened to be laid in our direction. Each explosion released more energy in a few seconds than the sun will produce across its entire 10 billion year life. The blast wave from one supernova can sweep interstellar gas outward for tens of light years. 15 of them, spaced out over millions of years, each pushing the same expanding shell a little further, produce exactly the cavity we now find ourselves sitting in. The bubble is still expanding at something like 6 or 7 kilometers per second. And here is the detail that turns the whole thing from astronomy into something closer to a crime scene. All of the gas swept up by those explosions had to go somewhere, and it piled up into a dense shell around the cavity's surface. Dense gas collapses. Collapsing gas forms stars. Every single one of the nearby star-forming regions astronomers have cataloged sits on the surface of this bubble, not scattered around it, on it. Taurus, Ophiuchus, Lupus, Corona Australis, Chameleon. Nurseries where new stars are lighting up right now. All of them arranged on the inner wall of a 14 million year old blast crater, because that is where the debris ended up. The explosions did not simply destroy. They plowed the field, which is a cheerful thought until you remember what plowed the field the sun grew in. The sun's position is the coincidence. It did not form here. It has been orbiting the galactic center for 4.5 billion years, minding its own business, and it wandered into this cavity roughly 5 million years ago, entirely by chance, and is currently passing near the middle of it. In another few million years, it will be out the other side. We are tourists in someone else's disaster. There is physical evidence for some of these explosions, and you can hold it in your hand. On the floor of the Pacific Ocean, in slow-growing crusts of ferromanganese, researchers have found deposits of an isotope called iron-60. It has a half-life of about 2.6 million years, which means every atom of it originally on Earth decayed away billions of years ago. Any iron-60 in a young seabed layer arrived from outside. Supernovae manufacture it. When one goes off within a few hundred light years, the debris eventually washes through the solar system and a thin dusting settles into the sediment. The ocean crust shows 2 clear signals, one peaking around 2.5 million years ago and an older one somewhere around 6 to 8 million. The same isotope has been found in lunar soil samples returned by Apollo, which rules out any purely terrestrial explanation. 2.5 million years ago, there were hominins walking around East Africa. Homo habilis, early Homo erectus, stone tools, the beginnings of everything we came from. And while they were doing that, a star somewhere within a couple of hundred light years collapsed and detonated, and the light of it would have been bright enough to read by at night for weeks. Nobody wrote it down. There was nobody who could. Some researchers, Adrian Malott among them, have argued that the radiation from that event may have raised cosmic ray levels at ground level enough to matter biologically, and have linked it, cautiously, to the marine megafauna extinction of the same era. The evidence is suggestive rather than settled, and I would not oversell it. But the timing keeps showing up in the sediment, and the sediment does not have an agenda. The bubble is not sealed, either. Above and below the galactic plane, it opens out into what has been called the local chimney, two vents where the hot gas escapes upward and downward into the galactic halo. You're in a room with the ceiling and the floor removed, venting into a space so large that the word room stops applying. That is the architecture of your neighborhood. Inside the big cavity, there are smaller structures, and one of them is currently wrapped around the solar system. It is called the local interstellar cloud, and less formally the local fluff, which is the sort of name astronomers give things when they are tired. Roughly 30 light years across, about 3/10 of an atom per cubic centimeter, temperature in the region of 7,000 Kelvin. The sun entered it somewhere between 10 and 20,000 years ago. Get the timing of that. The sun drifted into this particular cloud around the end of the last ice age, while humans were painting animals on cave walls in southwestern France and figuring out agriculture. Every recorded event in human history has taken place while the solar system was inside this one small wisp of gas. We will be out of it in another 10 or 20,000 years, and nobody knows precisely what is next door. There's a candidate. Immediately adjacent sits something called the G cloud, denser than the fluff, and it happens to contain Alpha Centauri. When the sun crosses into it, the pressure of the surrounding medium goes up, which squeezes the heliosphere inward, which lets more galactic cosmic radiation reach the planets. The shield is not a constant. It gets thicker and thinner depending on which part of the galaxy we happen to be wading through. There is a serious hypothesis, argued for decades and still unresolved, that these transits leave marks in the geological record. Denser cloud, compressed heliosphere, more cosmic rays reaching the atmosphere, more cloud nucleation, cooler climate. Some researchers have tried to line up ice ages with the sun's passage through galactic spiral arms. The correlations are tantalizing and the mechanisms are contested. I mention it because the idea itself is remarkable, whether on a planet, set by geography in a galaxy. So take stock of where you actually are. Inside a 30 light-year wisp of warm hydrogen. Inside a 300 light-year cavity blown open by 15 exploding stars, vented top and bottom into the galactic halo, on the inner surface of which new suns are currently igniting out of the debris. Every one of those layers was made by something ending violently. This is the quiet part of the galaxy. Which brings up a fact I find genuinely unsettling, and it is a matter of arithmetic rather than mood. There's a star called Betelgeuse, about 500 light years away, in the shoulder of Orion. It is enormous, unstable, and it will explode. Possibly tonight, possibly in 100,000 years, and possibly it already has and the light has not reached us. 500 light years is far enough to be safe. It is close enough to cast shadows on Earth at night. The rough consensus is that a supernova needs to go off within about 30 light years to seriously damage a planet's biosphere, mostly by stripping ozone and letting ultraviolet through. Nothing that big is currently that close. But the sun is moving, the other stars are moving, and everything in the galaxy is rearranging itself on timescales of millions of years. Nobody has a permanent address. Nobody gets a guarantee about the neighbors. It gets stranger the further you zoom out. The local bubble sits inside a larger web of similar cavities and shells produced by generations of dead stars pushing gas around, and the whole disk of the Milky Way is riddled with them. Astronomers have started describing the interstellar medium as a foam. Bubbles inside bubbles, walls where the debris piles up, new stars igniting along the seams. structure built entirely out of destruction. You are floating in one of the empty pockets of that foam. It is the emptiest room available, and it exists because things died here. The hydrogen brushing past you was blown out of a star that no longer exists by an explosion that occurred before there was anything on Earth recognizable as a person. Every particle in this cavity is debris, and the cavity itself is the shape of the wound. So does the sun, incidentally. It is doing to the galaxy what those 15 stars did, on a smaller and much gentler scale, blowing its own little bubble into the fluff with a wind that will keep blowing for another 5 billion years. And then it will bloat, shed its outer layers, and leave a hot white cinder surrounded by a slowly dissipating shell of everything it ever had. But that is billions of years away, and right now the sun is still doing what it has always done, which is burn 600 million tons of hydrogen per second in a core at 15 million degrees, throwing out light in every direction, including this one. Some of that light is arriving at your body at this exact moment, and it is the last light from home you're ever going to receive. So turn around. It is worth doing. Somewhere in that field of hard, unblinking points, one of them is brighter than the others, and everything you have ever known is inside it. Every person, every argument, every city, all of human history, folded down into a single dot of light with no visible width. It will not look like anything. That is the part that gets people. From a surface of Earth, the sun is the brightest object anyone has ever looked at, and it is not close. Astronomers rate brightness on a magnitude scale where lower numbers mean brighter, and the sun sits at negative 26.74. The full moon manages negative 13. Venus at its best gets to negative 4.9. The scale is logarithmic, so those gaps are not small differences. The sun outshines the full moon by a factor of 400,000. Brightness falls with the square of distance. Double the distance, and you get a quarter of the light. It is a simple rule, and it is merciless over interstellar spans. From Jupiter, 5 astronomical units out, the sun is already 25 times fainter, still far too bright to look at directly. From Neptune, it is 900 times fainter, and noon is roughly as bright as a heavily overcast dusk. Keep going. At the heliopause, 120 astronomical units out, the sun is still a searing pinprick, painful to look at, casting real shadows. It is only when you get to genuinely interstellar distances that it starts behaving like a star. At 1 light year, which is 63,000 astronomical units, the sun would shine at about magnitude negative 2.7. Sit with that number for a second because it is oddly beautiful. Negative 2.7 is about as bright as Jupiter at its best in an Earth sky. Brighter than Sirius. A striking, obvious object that would draw the eye immediately and cast the faintest shadow on a white surface. 1 light year out, the sun is the finest star in the sky, and it is already only a star. At the distance of Proxima Centauri, 4¼ light years, the sun drops to roughly magnitude 0.4. That is an ordinary bright star, comparable to Procyon or Altair, something you would learn the name of in a stargazing app and then forget. Anyone standing in that system and looking back at us would see a nice yellow star in the constellation Cassiopeia, sitting off the end of the W, unremarkable in every way. And it disappears completely at about 56 light years. That is the arithmetic. The naked eye limit under perfect conditions is around magnitude 6, and the sun falls below it at roughly 17 parsecs. There are something like 1,300 star systems inside that radius. Beyond it, in a galaxy of a few hundred billion stars, our sun is not merely unimpressive. It is invisible without a telescope. The Earth goes long before the sun does. It goes almost immediately. A planet produces no light of its own. It only reflects, and it reflects about 30% of what falls on it. From Mars, Earth is a bright blue evening star. From Jupiter, it is a faint dot lost in the glare. Past Saturn, it is effectively unobservable by any human eye because the sun sits right next to it and drowns it. which is why the most important photograph in the history of the species almost never got taken. In the late 1980s, Voyager 1 had finished its planetary work and was heading out of the solar system with a functioning camera and nothing left to point it at. Carl Sagan had an idea: turn the spacecraft around and take a picture of home. There was no scientific value in it, and everyone involved knew that. The engineers pushed back for years, and their reasons were good ones. Pointing the camera near the sun risked frying the Vidicon tubes. Slewing the spacecraft cost fuel and time. The mission's priority was the particle instruments, and the camera would have to be shut down permanently afterward to save power for them. Sagan kept asking anyway. He asked for most of the decade. He got on February 14th, 1990. Voyager 1 was 6.06 billion kilometers out, about 40 astronomical units, and it turned and took 60 frames, a mosaic covering most of the solar system. A family portrait, 6 planets in one sequence from outside. Then the cameras were switched off for good, and they have never been switched on again. In one of those frames, there is a pale blue speck. It occupies about 0.12 of a single pixel, less than 1 pixel. It is caught inside a scattered beam of sunlight, a lens artifact, a diagonal band of light across the image that happens to fall exactly where the Earth is, which is a coincidence so perfect that people accused NASA of faking it. That speck is the planet. Every human being who has ever lived, except for 24 who went to the moon, was inside that speck when the shutter opened. Every war, every empire, every language, every religion, every piece of music, every person you have loved or hated or failed to notice. All of it inside a smear of blue light 12% of the width of 1 pixel, taken by a machine the size of a car from 4 light hours away. Sagan wrote about it 4 years later, and the passage is famous for good reason, so I will not recite the whole thing. The line that stays with me is the one about the dot being the only home we have ever known, and about how our posturings and our imagined self-importance are challenged by that point of pale light. He was dying of cancer when he wrote it. He knew what he was doing. For light hours, that was the distance. From where you are floating, the number is not hours. Light from the sun took years to reach your face, so the star you're looking at is a recording. If you're 10 light years out, you're seeing the sun as it was a decade ago, and if something happened to it since, the news is still on its way and will not arrive early. That is true of everything in your sky. In fact, nothing you can see is current. Sirius is 8.5 years out of date. Betelgeuse is 5 centuries behind. The Andromeda Galaxy, which is the furthest object visible to an unaided human eye, is showing you light that left before there were any humans to leave for. You're not looking at a sky. You're looking at a filing cabinet. It does something to the idea of home, being able to point at it. On Earth, distance always came with a route. However far away a place was, there was in principle a way to get there, a road, or a flight path, or a boat. From here, there is no route. You can point at the sun with a finger, and the gesture is complete and useless. Direction without a mechanism. And it will get fainter. You are still moving, and inheriting the velocity you arrived with means the number in your sky keeps climbing. Magnitude -2, then 0, then 2, then 4. Every year the light from home arrives a little thinner. There is no dramatic moment when it goes out. It simply becomes one of the fainter stars, and then it becomes indistinguishable, and then it is gone. Something similar happened in 1968 in reverse, and it is worth putting next to the pale blue dot because they're the same photograph taken from different ends of the story. Apollo 8 came around the far side of the moon on Christmas Eve, and Bill Anders grabbed a camera and shot the Earth rising over the lunar horizon in color. Nobody had planned that shot either. It was not on the flight plan. Earthrise showed a world with weather on it. Clouds, oceans, a visible curve, something you could imagine walking on. 22 years later, the same planet had been reduced to a fraction of a pixel. Both images are of home, and only one of them still looks like a place. Somewhere between those two distances, Earth stops being a location and becomes a coordinate. There is a genuine psychological literature on this, and it has a name. The overview effect, coined by Frank White in 1987, describing what astronauts consistently report when they see the whole planet at once. A sudden and involuntary collapse of the importance of borders, a feeling of protectiveness, occasionally something close to grief. Michael Collins described it. Rusty Schweikart described it in detail, and it changed the direction of his life. Nobody has studied what happens when the planet is too small to see, because nobody has been out here. Psychologists working on future Mars missions have given it a provisional name, and we will come back to it properly later because it deserves its own chapter. For now, understand that the overview effect requires a view. You do not have one. You have a point of light and a memory of what is inside it. The sun is also, from out here, extremely ordinary. That is worth dwelling on. It is a G-type main sequence star, about 70% hydrogen, roughly 4.5 billion years old, sitting almost exactly in the middle of its life. There are billions like it in this galaxy alone. Roughly 3/4 of all stars are the smaller, dimmer red dwarfs, so the sun is actually on the brighter side of average. That is the best you can say for it. It has no distinguishing feature. Nothing about its spectrum, its mass, its rotation, or its position would attract attention from an astronomer anywhere else in the galaxy. If an alien survey were cataloging nearby stars, it would receive a number and a line in a table. The only remarkable thing about the sun is entirely local and entirely accidental. It happens to be the one that made you. So look at it while you can. It is one point among thousands, slightly brighter than its neighbors, and its light is 8 minutes old by the time it leaves the solar system and years old by the time it reaches you. Nothing about the view tells you anything is there. No hint of the planets, no trace of the biosphere, no signal at all that 4 billion years of life happen around it. That cuts the other way too, and it is the part that will matter later. Every one of those other points you're looking at could have exactly the same secret. A planet with oceans, a biosphere, a species that got as far as making machines and asking questions. From out here, you would never know. The view is identical either way. Whatever is happening out there is happening below the resolution of anything you could do about it. And now the sun is going to slip below the threshold of your vision, and you'll have to make do with what is left, which is starlight, and only starlight, and less of it than you think. Human eyes are exquisite instruments in the dark, better than most people realize, and they're about to be pushed to the absolute limit of what a biological detector can do. There are about 120 million rod cells in the back of your eye, and almost none of them have ever been properly used. They are the night machinery, roughly 1,000 times more sensitive than the 6 million cones that handle daylight and color, and modern human life keeps them permanently switched off. Out here, they finally get their moment, and what they show you is not what you would guess. Dark adaptation is a chemical process, and it is slow. The pigment in your rods, rhodopsin, gets bleached apart by light and has to be rebuilt molecule by molecule. The first big improvement comes in about 5 minutes. Full sensitivity takes 20 to 30, and for some people closer to 40. Astronomers guard it obsessively, using red flashlights and swearing at anyone who opens a car door, because one careless white light resets the whole clock. By the end of that process, your eye is one of the most sensitive light detectors in the known universe. In 1942, 3 researchers, Selig Hecht, Simon Schler, and Maurice Perrin, sat volunteers in the dark and fired precisely counted flashes at them, and worked out that a dark, adapted human being can reliably detect somewhere between 5 and 14 photons. Not 5 and 14,000 individual particles of light, arriving at the back of a wet biological eye. Later work went further. A 2016 experiment out of the University of Illinois, using a source that emitted single photons on demand, found that people could pick out one photon at a rate slightly better than chance. 1. It is at the theoretical floor of what any detector can do, and it is sitting in your skull, and it took a species several 100,000 years to notice. There is a catch, and it is a strange one. Your rods are distributed across the retina everywhere except the center. The fovea, the small patch you use for reading and for looking directly at things, is packed with cones and contains essentially no rods at all. So in true darkness, there is a blind spot at the exact center of your gaze. Look straight at a faint star and it vanishes. Look slightly beside it and it comes back. Amateur astronomers call the workaround averted vision, and it becomes a reflex after a few nights. You learn to look past things in order to see them. Out here, it would govern your entire experience of the sky, because everything in it is faint. You would spend your last minutes of consciousness deliberately not looking at the things you were trying to look at. Color goes too, and the way it goes is subtle. Rods have no color discrimination whatsoever. They peak in sensitivity at around 507 nanometers in the blue-green. So as light levels fall, blues stay visible longer while reds drop away first. Jan Perkinji described this in the 1820s after noticing that red flowers in his garden went black at dusk while blue ones held their tone. Everything out here is gray. Structured, detailed, and completely gray. Now the illumination budget, which is where it gets bleak. Direct sunlight on Earth delivers about 100,000 lux. An office is 500. A full moon manages a quarter of a lux, which is enough to walk by. Starlight alone, on a perfect moonless night at a perfect dark site, comes to roughly 2/10,000ths of a lux. That is the entire lighting rig for the rest of your existence. Except out here, it is a little brighter than that, which surprised me when I worked it out. Earth's atmosphere absorbs and scatters a real fraction of incoming starlight, and it adds its own faint interference on top. Air glow from oxygen and sodium in the upper atmosphere, permanent and unavoidable, which on a dark night contributes more light than all the stars combined. Remove the air and you remove both problems. So the sky you have is sharper and deeper than any sky in human history. No twinkling, because scintillation is turbulent air bending starlight, and there is no air. No extinction near the horizon, because there is no horizon. Stars visible down to fainter magnitudes than any observer on Earth could reach unaided, possibly twice as many as the 4,000 or 5,000 a person can see from a mountaintop on the clearest night of the year. And across the middle of it, the galaxy. Not the pale smear you may have seen once on a camping trip. From here, the Milky Way is a structure, a band of concentrated starlight with visible internal detail, bright enough that it is the dominant feature of your entire visual field. On Earth, at genuinely dark sites, the galactic core alone can cast a faint shadow. Out here, that is more true, not less. Running down the length of it are the tiers, dark lanes and gaps that look torn out of the band, the biggest of them stretching from Cygnus down through Aquila and Sagittarius. Early sky watchers assumed those were empty gaps between stars. They are the opposite. They are clouds of interstellar dust, thick enough to block the light of everything behind them, sitting between you and the crowded middle of the galaxy. Which produces one of the facts I find hardest to shake in all of astronomy. You cannot see the center of your own galaxy. Not with the eyes. Not from here, not from anywhere in the disk. The dust between us and the galactic core absorbs visible light so effectively that the core is dimmed by something like 30 magnitudes, a factor of 1,000,000,000. It is the largest, brightest, most crowded structure within 100,000 light years, and it is permanently hidden. We only know what is in there because infrared and radio waves pass through dust where visible light cannot. That is how the supermassive black hole at the center was found, by watching stars whip around an invisible mass of 4 million suns in infrared over decades, work that won Andrea Ghez and Reinhard Genzel a Nobel Prize in 2020. Your eyes will never see it. The instrument is the wrong wavelength. Look for the planets, and there is nothing. They are gone completely, all 8 of them, along with every moon and every asteroid, because a planet at interstellar distance reflects an unmeasurably small amount of light. Jupiter, the largest object in the solar system besides the Sun, disappears from naked eye view within a handful of astronomical units. The entire architecture you grew up inside has collapsed into one point. What about your own body? This is the detail I keep returning to. Under 2/10,000ths of a lux, a dark adapted, I can just barely resolve a large nearby object, so you would be able to make out the shape of your hand held in front of your face. Gray, edgeless, without detail. Enough to confirm that you're still there, and nothing else within 4 light years would be visible at all. There's also no shadow of you, because there is no single dominant light source. Light arrives from every direction at once. Thousands of point sources spread across the whole sphere, so nothing casts a defined shadow. On Earth, you have never once been in a lighting situation like that. Every environment you know has a sun or a lamp or a window in a direction that the light comes from. Out here, there is no direction. There is only ambient. Now for the thing that actually unnerves me about darkness, and it has nothing to do with what is out there. Close your eyes in a pitch black room, and you do not see black. You see a dim, faintly textured gray, restless, with slow shapes moving through it. German psychologists named it Eigengrau, meaning intrinsic gray, and it is the noise floor of your visual system. It comes from your rods misfiring. Rhodopsin molecules occasionally isomerize from thermal energy alone, with no photon involved, and each false alarm looks to the brain exactly like a real detection. Your retina is a detector so sensitive that its own body heat trips it. Perfect darkness is not something your eye can report, because the eye is always producing a signal, and in the absence of light, that signal is all there is. Give that system nothing to do for long enough, and it escalates. There is a documented condition called Charles Bonnet syndrome, in which people who lose their sight begin to experience vivid, detailed, fully formed visual hallucinations. Patterns, faces, figures, entire scenes, all of it in perfect clarity, all of it manufactured. They know it is not real. That does not make it stop. The visual cortex, starved of input, begins generating its own. So the sky out here would eventually populate itself, not with anything real, with whatever your occipital lobe assembles out of noise and memory and expectation, in a place with no reference points to correct it. There is no way to check. There is nothing to compare suspicion against. Every perception you have from now on arrives without a second opinion, which is worth pausing on, because there is a question hiding underneath this chapter that nobody usually asks. Why is the sky dark at all? Put an infinite number of stars in an infinite universe, and every line of sight should eventually hit one, and the whole sky should blaze like the surface of a star. Astronomers argued about it for centuries and attached Johann Olber's name to the paradox. The answer, worked out properly only in the 20th century, is that the universe has an age and an expansion. Light from far enough away has not had time to arrive, and light from beyond a certain distance is stretched by expansion into wavelengths your eye cannot register. The darkness between the stars is the shape of the universe's youth. Every gap in that sky is a place the light has not finished crossing. It is also, I would argue, the only genuinely beautiful thing in your situation. You are in the best seat any human being has ever occupied for looking at the universe. No atmosphere, no light pollution, no clouds, no dawn coming to end the session. An unobstructed view of 200 billion stars with fully dark adapted eyes in the middle of the emptiest region in the neighborhood. And you get about 15 seconds of it. That is the joke the universe is telling, and I do not think it is a kind one. The finest observing conditions in the history of vision, handed to a set of eyes that will be unconscious before dark adaptation has even begun. 20 to 30 minutes to adapt. 15 seconds of consciousness. The numbers do not overlap anywhere. So the view is theoretical, and I have been describing something no one will ever actually see, which is fine, in a way, because there is one sense that keeps working long after the eyes have given up, and it does not need a photon or a working retina or a functioning brainstem to do its job. It only needs a body, and what it delivers out here is worse. Because there is no sound in interstellar space. Everybody knows that sentence, and almost nobody has thought about what it means from the inside. It does not mean quiet. It does not mean muffled. It means that the only pressure waves reaching your inner ear are the ones your own body is generating, and your body generates a great many of them, all the time, and you have never once heard them without competition. Sound is a rumor pass between molecules. You speak, your vocal folds shove the air. That shove propagates outward as a pressure wave at 343 meters per second, and eventually it jostles somebody's eardrum. Every sound you have ever heard worked that way. Remove the molecules, and you have not made the world quiet. You have removed the mechanism entirely. This is why the vacuum bell jar demonstration is the most quietly disturbing thing in a school science curriculum. You put a ringing alarm clock inside a glass dome and pump the air out, and the ringing fades away to nothing while you can still watch the hammer striking the bell. The mechanism is working perfectly. The sound has simply lost its road. Robert Boyle ran a version of that experiment in the 1660s, and it unsettled people then too. There are about 1/10 of an atom per cubic centimeter out here, which is technically enough to carry a pressure wave, in the same way that a single grain of sand every 10 kilometers is technically a beach. Interstellar plasma does support waves, and astronomers do detect them, at frequencies measured in cycles per million years and wavelengths measured in light years. Nothing in that description is going to reach your ear. So the outside world has gone completely silent, and one sound source remains. You. This is where the chapter stops being physics and starts being unpleasant, because a human body is a genuinely noisy machine, and you have spent your entire life with that noise buried under everything else. We know exactly what it sounds like because there are rooms on Earth quiet enough to find out. In 2004, a facility in Minneapolis called Orfield Laboratories had its anechoic chamber measured at 9.4 decibels below zero. 0 decibels is defined as the faintest sound a healthy young ear can detect. That room is below the threshold of human hearing, held up by heavy concrete, steel, and layered fiberglass wedges that eat any reflection. Microsoft built a quieter one in 2015 at its Redmond campus, measured at 20.6 decibels below zero, which is close to the theoretical limit, because at that point the noise you are fighting is the thermal jostling of air molecules themselves. The room floats on vibration isolating springs. It has 6 nested layers of shell. Building it took 18 months, and the point of it was to test how quietly a laptop fan runs. People who go into those rooms describe the same progression, and it happens fast. First, the absence, which feels like pressure in the ears, like altitude. Then the heartbeat, which arrives within seconds and is much louder than anyone expects. Then the breathing, which sounds industrial. Then the blood, a soft, rhythmic surge in the ears, a sound most people have never once consciously registered in their lives. Then it gets specific. Joints clicking, the muscles in your neck creaking as you turn your head, your stomach going about its business in detail, the sound of your own scalp moving. Stephen Orfield, who runs the Minneapolis lab, has said that visitors have to sit down because standing becomes disorienting since the brain uses reflected sound for balance without ever mentioning it to you. There's a widely repeated claim that nobody can stay in the Orfield chamber longer than 45 minutes. It is a good line, and the evidence for it is thin, more anecdote than study, so I would not lean on it. What is well documented is that people find it deeply uncomfortable, that discomfort arrives quickly, and that almost everyone asks to come out earlier than they intended to. Then there's the part that genuinely surprised me. Your ears emit sound, not metaphorically. In 1978, a British researcher named David Kemp demonstrated that the inner ear generates its own faint acoustic output, produced by the hair cells in the cochlea actively flexing, and it can be measured with a microphone in the ear canal. It is called an otoacoustic emission, and roughly 1/3 to half of healthy people have spontaneous ones. Which means that in a sufficiently quiet environment, a meaningful fraction of the population would be able to hear the noise their own ears are making. A faint, pure tone generated by the organ that is listening for it. That is a closed loop with nothing outside it, and it is a reasonable description of your entire remaining sensory life. Most people would also hear tinnitus, which is nearly universal in silence. Studies going back to the 1950s put volunteers in soundproofed rooms and found that the large majority reported a ringing, hissing, or high whine within a few minutes. The tone was always there. Ordinary background noise was covering it. Take the world away, and the ringing is what remains, permanent, unmaskable, at the front of everything. Now, push it further, because researchers already have. In 1951, a psychologist named Donald Hebb at McGill University in Montreal began paying student volunteers $20 a day to do nothing at all. That was serious money in 1951. The task was to lie on a comfortable bed in a lit cubicle wearing translucent goggles, cotton gloves, and cardboard tubes over the forearms with a constant hum masking sound. No input, no structure. Most of them expected easy money and time to think. Almost none of them lasted the intended week. Within a day, volunteers reported being unable to hold a thought, unable to concentrate, unable to do simple arithmetic. Their sense of time collapsed, and within 24 to 48 hours, a large fraction of them began hallucinating, first as drifting dots and geometric patterns, then as full scenes with figures moving in them. The reports include marching squirrels with sacks over their shoulders, rows of eyeglasses walking down a street, prehistoric animals in a jungle. The volunteers knew none of it was real, which did not help. Some of them found it entertaining and then found it frightening, and several quit early and refused to come back for money they badly wanted. It is worth knowing where the funding came from, because it complicates the picture. Hebb's work was supported by the Canadian Defense Research Board, and the results fed directly into the interrogation research programs of the era, including material that ended up in American manuals. The finding that a human mind falls apart in the absence of input was interesting to psychologists and useful to other people. Both things happen at once. Around the same time, John Lilly at the National Institute of Mental Health was building the other version of the experiment, a tank of body temperature salt water in a dark soundproofed room where a floating person loses touch, gravity, sound, and light simultaneously. Lilly's early results matched Hebb's. His later career went into psychedelics and attempts to talk to dolphins, and the science got considerably looser, but the tanks worked. Modern replications have been tighter, and the results are, if anything, faster. In 2009, Oliver Mason and Francesca Wong put healthy volunteers in a completely dark, completely silent room for 15 minutes. 15. Nearly all of them reported perceptual distortions. A substantial fraction reported hallucinations, faces in the dark, sensations of presence, paranoid thoughts. The scores on standard psychosis screening scales went up measurably in a quarter of an hour. There is a much larger and much grimmer body of evidence, which is the literature on solitary confinement. Stuart Grassian, examining prisoners in Massachusetts, described a consistent cluster of symptoms severe enough that he argued it constituted a distinct psychiatric syndrome: hypersensitivity to noise, perceptual distortions, hallucinations, panic, difficulties with impulse control. Craig Haney's work at Pelican Bay found rates of these symptoms far above the general prison population. And those prisoners have gravity, air, light, meals, a floor, a schedule, and the sound of other human beings somewhere in the building. Every single one of those is a form of input, and the loss of them is what damages people. Strip all of it away, simultaneously, permanently, with no possibility of anyone arriving, and there is no experimental literature at all. Nobody has ever been in your condition and reported back. There is one more thing missing out here that nobody thinks about, and it is proprioception's partner. Your vestibular system, 3 fluid-filled loops in each inner ear, tells you which way is down by sensing the pull on the fluid. In free fall, the fluid stops pulling in any direction. It is why new astronauts spend their first days in orbit nauseous and reaching for handholds that are not there. Down stops existing as a concept. So take the full inventory of what has been switched off. Sound entirely. Touch, apart from your own body against itself. Smell and taste, gone with the air. Balance, absent. Sight, functional, delivering a gray and mostly static field. Temperature sensation, confused. Time, unmarked by any external event. That is the sensory environment, and it is the least varied one any conscious being has ever occupied. The brain does not tolerate that. It is fundamentally a prediction engine, built to compare what it expects against what arrives, and it will not sit idle when nothing arrives. It turns the gain up. It starts treating internal noise as external signal. Then it builds a world out of that noise, because a world is what it does, and it has nothing left to build one from except you. I keep thinking about the specific texture of it. Not screaming, not terror, not anything cinematic. A person floating in a gray field, hearing their own pulse in a high-thin tone, listening very carefully to nothing, and gradually becoming certain that they can hear something else. That is the actual experience on offer, and it lasts as long as consciousness does. And there is nothing you can do to break it. That is the structural fact underneath the whole chapter. You could shout with everything you have and produce no sound at all outside your own skull. You could set off an explosion beside you and hear nothing. There is no configuration of effort, intelligence, or luck that generates a single decibel out here. Silence in this place is not a condition. It is a law. Unless someone comes, that is the only mechanism left, and it is worth taking seriously for a moment, because the galaxy is not empty of stars, and the nearest one is visible right now from where you're floating. It has a name and a planet, and it has been sitting in the southern sky of Earth for as long as anybody has been looking up. Proxima Centauri, for 0.24 light years away, which is close enough that we have measured its planets and argued about their atmospheres. In the language of the galaxy that is next door, practically touching, an insignificant hop. In the language of anything that has ever been built or ever will be, it may as well be on the other side of the observable universe. A light year is a unit designed to make distance manageable, and it fails completely at its job. Light covers 300,000 kilometers in a second, which is 7.5 laps of the Earth. Give it a full year, and it covers 9.5 trillion kilometers. The number is so large that it stops being a quantity and becomes a texture, and that is exactly the problem with it. So try smaller units and work up. Light takes 1.25 seconds to reach the moon, 8 minutes and 20 seconds to reach Earth from the sun, 43 minutes to reach Jupiter, 5.5 hours to reach Pluto, about 22 hours to reach Voyager 1. Then the next meaningful thing in that direction is 4.25 years away, and the scale simply breaks. Proxima Centauri sits at 4.24 light years, which comes to about 40 trillion kilometers, or 268,000 astronomical units. Put another way, the distance from the Sun to Neptune, laid end to end, 9,000 times, is the closest star to our own, and there is nothing between here and there. Nothing at all, apart from 1/10 of an atom per cubic centimeter. Scale models help, so here's the one I like. Shrink the Sun to a grapefruit, 10 centimeters across, sitting on a table. Earth becomes a grain of sand less than a millimeter wide, orbiting 11 meters away across the room. Jupiter is a large pea at 55 meters. Neptune is a peppercorn 330 meters out at the far end of a long field. On that same model, where the whole solar system fits inside a few city blocks, Proxima Centauri is 2,900 kilometers away. That is roughly the distance from London to Cairo. 2 grapefruits, one in a room in England and one in Egypt, and absolutely nothing between them but a few grains of dust. That is the actual density of matter in your galaxy. Now put a real vehicle on that map. Voyager 1 is the fastest object ever to leave the solar system, moving at about 17 kilometers per second relative to the Sun, which is 61,000 kilometers an hour. It would cross the continental United States in about 4 minutes. It covers the Earth-Moon distance in 6 hours. By every human standard, it is unimaginably fast. At 17 kilometers per second, a single light year takes about 17,500 years. Proxima Centauri, if Voyager were aimed at it, would take around 74,000. Which brings up the joke buried in the mission. Voyager 1 is not aimed at anything. In roughly 40,000 years, it will pass within about 1.5 light years of a dim star called Gliese 445, and that is the closest it ever gets to a destination. 74,000 years. Let me anchor that because it is a number people nod at without hearing. 74,000 years ago, Mount Toba erupted in Sumatra in one of the largest volcanic events of the last 2 million years. Anatomically modern humans existed, but had not yet spread widely out of Africa. Neanderthals were still alive and would be for another 40,000 years. There was no agriculture, no writing, no wheel, no cities. Launch a Voyager-class probe at Proxima Centauri when the first Homo sapiens were walking out of the Rift Valley, and it would be arriving roughly now. That is the travel time to the nearest star with the best hardware our species has ever flown. Not to a good star, not to an interesting one, to the closest possible one, a dim red dwarf too faint to see with the naked eye from Earth. And Voyager has not even left the solar system properly, depending on where you draw the line. Past the heliopause, there is still the Oort cloud, a spherical shell of frozen debris held loosely by the sun's gravity, beginning somewhere around 2,000 astronomical units out and extending, by some estimates, to 100,000. Voyager will take about 300 years to reach the inner edge, around 30,000 years to come out the far side. 30,000 years just to clear the sun's gravitational suburbs. Written language is about 5,000 years old. Everything we would recognize as civilization fits into the last 12,000. The sun's junk drawer is more than twice as deep, measured in time, as the entire human project. And the Oort cloud is where you would still be if you had not been dropped somewhere much further out. Could we go faster? Yes, a little, and it is worth knowing exactly how much. The Parker Solar Probe holds the outright speed record for a human object, hitting about 690,000 kilometers an hour as it whipped past the sun. That is 192 kilometers per second, 11 times Voyager's pace. And it is achieved by falling toward a star rather than by going anywhere. Even at that absurd velocity, sustained the whole way, Proxima Centauri is about 6,600 years out. 6,000 years is the distance in time back to the invention of the plow. Sustained the fastest speed any human machine has ever reached for 60 centuries, and you arrive at the nearest star. And nobody has any idea how to sustain it, because Parker is only that fast for a few hours at perihelion. Crewed vehicles are slower still. The record for humans belongs to Apollo 10, which touched roughly 39,900 kilometers an hour on its return from the moon in May 1969. That is 11 kilometers per second, still the fastest 3 people have ever traveled, set 57 years ago and unchallenged since. At Apollo 10's speed, Proxima Centauri is 114,000 years away. There is exactly one proposal on the table that gets a human-made object to another star inside a human lifetime, and it works by giving up on the idea of a ship. Breakthrough Starshot, announced in April 2016 with $100 million behind it, would build a ground-based laser array of roughly 100 gigawatts and use it to push a gram-scale chip on a 4-meter sail up to 20% of the speed of light. 20% of light speed gets you to Proxima in about 20 years, plus 4 and a bit more for the pictures to come back. The engineering problems are severe. A laser array with the output of 100 nuclear plants firing for minutes, a sail that survives it, a chip that survives dust impacts at 60,000 kilometers per second, and no way whatsoever to slow down at the other end. It flies through the system in hours. Note what is absent from that plan. Any person, every serious interstellar concept eventually arrives at the same conclusion, which is that you do not send bodies. Bodies need water, air, food, shielding, gravity, and psychological maintenance. and each of those multiplies the mass, and mass is the thing you cannot afford. The galaxy is open to postcards and closed to passengers. Radio is the one thing that crosses the gap at a survivable cost, and even radio is slow. A message from where you are to Proxima Centauri takes 4 years and 3 months. A reply takes the same again. The shortest possible conversation with the nearest star, one question and one answer, runs 8.5 years. There's no such thing as a real-time conversation anywhere outside a single solar system. Widen the frame, and it gets worse in a hurry. The Milky Way is about 100,000 light-years across. Voyager 1, at 17 kilometers per second, would need roughly 1.7 billion years to cross it, which is more than a third of the age of the Earth. The nearest large galaxy, Andromeda, is 2.5 million light-years out. Those are not travel distances. They are geological facts. And you are not moving toward any of it. That is the specific thing about your situation that I want to be clear about. Whatever velocity you arrived with, you keep in whatever direction you happen to be pointed forever. There's no course. There is no destination. You're not traveling to somewhere in the way that word normally implies. You're simply continuing. Which means the odds of hitting anything are worth computing, and they are absurd. The average distance between stars in this part of the galaxy is around 5 light-years. Stars are roughly 1 million kilometers across. The ratio between the size of the objects and the space between them is about 10 million to 1. Fire a body in a random direction, and the chance of ever coming near anything is effectively 0, and it stays 0 for the age of the universe. Galaxies collide, and the stars inside them almost never do, for exactly this reason. Andromeda is going to hit the Milky Way in about 4.5 billion years, and current models suggest the probability of any individual star colliding with another is close to nil. 200 billion stars pass through 200 billion stars, and nothing touches. The emptiness is that good. There's a specific loneliness in that arithmetic that I do not think has a name. It is not the loneliness of being far from help. It is the loneliness of being in a place where the concept of help does not have a mechanism. Distance on Earth was always a matter of time and money and effort. Out here, it is a matter of physics, and physics does not care how badly you want to be otherwise. Here is the version of the number that undoes me. If you could walk on foot at a steady 5 kilometers an hour without sleeping or stopping for where you are to Proxima Centauri, the trip would take about 900 million years. Complex life on Earth is roughly 600 million years old. You would have set out before there were animals. And Proxima is the good option. There are around 60 stars within 16 light-years of the Sun, and the great majority are dim red dwarfs, flare-prone and stingy with heat. The nearest star meaningfully like the Sun is Tau Ceti, 12 light-years out. Even if there were somewhere worth arriving at, and there might be, the arriving is the part that no amount of cleverness has yet found a way around. So the honest summary of your position is this. You are in a place that nothing can reach you across, that no signal can usefully cross, and that no vehicle humanity can conceive of could carry a person out of. The distances are not obstacles to be beaten with better engineering. They are the answer to the question, and the answer is no. Which makes it strange that you're being hit by something. Constantly. Right now, as you read this, particles are arriving at your body from every direction in the sky, having traveled thousands or millions of light years to get here, moving at very nearly the speed of light, and carrying more energy than anything a laboratory on Earth can produce. The distances stopped nothing. Something crosses the galaxy routinely, and it has been passing through your body your entire life at a slower rate. And out here, outside the Sun's bubble, the rate goes up by a factor of 4. The astronauts who went to the moon knew about this. They saw it happen with their eyes closed in the dark, and it frightened them. In 1912, an Austrian physicist named Victor Hess went up in a hydrogen balloon carrying an electroscope because he wanted to prove that background radiation came from the ground. Everyone assumed it did. Rocks were radioactive, so the higher you went, the less you should measure. He climbed to 5,300 meters, and the reading went up. Not down, up by a factor of several, and it kept climbing as long as he did. He flew at night to rule out the sun. He flew during a solar eclipse. Same result. Something was coming down from above, hard enough to punch through the atmosphere and into a sealed instrument, and it was not coming from any object in the sky that anybody could point at. Robert Millikan later gave the phenomenon the name that stuck, cosmic rays, and Hess got a Nobel Prize in 1936. They're not rays. That is a historical mistake we never bothered to fix. They are particles, bare atomic nuclei, stripped of their electrons, moving at close to the speed of light. Roughly 90% are simple protons, about 9% are helium nuclei, and the remaining 1% is everything else the periodic table has to offer, up to and including iron. That last 1% is the problem. Physicists call them Hz particles, meaning high atomic number and high energy, and a single iron nucleus traveling at 90% of light speed carries thousands of times the damage potential of a proton. There are not many of them. There do not need to be many. Out here, beyond the heliopause, the total flux of all of it runs at roughly 4 times what a spacecraft sees near Earth. Most of them were made by exploding stars. A supernova shock front acts as a natural accelerator, catching charged particles and slingshotting them back and forth across the shock until they carry energies no human machine can reach, then releasing them into the galaxy to wander for millions of years, bent and rebent by magnetic fields until all memory of their origin is lost. By the time one reaches you, it has no direction. It has no history you can read. Now, the part that turns this from a physics lecture into something a person can feel, and it starts with Apollo 11. On the way to the moon, in the cabin, with the lights out and his eyes closed, Buzz Aldrin saw flashes of light. Faint, brief, sometimes points, sometimes streaks. He mentioned it. Nobody had briefed him on it because nobody had expected it. Then it turned out that almost everybody was seeing them. Post-flight debriefs from later missions found that roughly 80% of Apollo crew members reported the flashes, at rates of 1 or 2 a minute in some cases, always in darkness, always with eyes adapted or closed. Some described white specks. Some described streaks with direction. 1 or 2 described something like a small starburst directly in the visual field. NASA took it seriously enough to build hardware. On Apollo 16 and 17, the crews flew something called the Apollo Light Flash Moving Emulsion Detector, a bulky helmet packed with photographic emulsion plates that a crewman wore while lying still in the dark and pressing a button every time he saw a flash. Ken Mattingly wore it. Ron Evans wore it. They looked ridiculous, and it worked. The emulsion recorded particle tracks. The button recorded reported flashes. When the plates were developed and the timings compared, the correlation was there. The flashes were cosmic rays passing through the astronauts' heads and interacting with their eyes. They were seeing individual subatomic particles, one at a time, using their own retinas as the detector. There are 2 explanations for the mechanism, and both are probably right in different cases. One is direct ionization. The particle physically slams through the retina, dumping energy into the photoreceptors and triggering them the way light would. The other is Cherenkov radiation, where a particle moving faster than light does in the jelly of your eye produces a genuine cone of blue light inside the eyeball. Actual photons generated inside your head by something arriving from outside the galaxy's arm. Astronauts on the space station still see them, though less often because Earth's magnetic field deflects the majority. They report them most during passes through the South Atlantic anomaly, a region where the inner radiation belt dips closer to the surface. Some describe them as flash bulbs at the edge of vision. Others describe them as unpleasant enough to make sleeping difficult. So follow one particle through your body and consider what it actually does. An iron nucleus arrives at, say, 80% of light speed. It does not bounce. It goes straight through, and along its path it rips electrons off every molecule it passes, leaving a narrow column of ionized wreckage a few micrometers wide and however many centimeters long. Cells along that track are killed or damaged. The track is called a microlesion. The difference from medical radiation matters here. An X-ray spreads its energy diffusely through a volume, and your body has repair machinery tuned for exactly the kind of scattered damage. An HCE particle concentrates everything along a line, destroying a contiguous run of cells and the DNA inside them all at once. Repair systems that handle single breaks, well, do badly with a whole column of them. That is why space radiation is not simply more radiation. Neurons are the worst case because you do not grow new ones in most of your brain. A team led by Charles Lamolli at the University of California, Irvine, has spent years firing simulated cosmic rays at rodents and then testing them, and the results are consistent and grim. Reduced complexity in the branching of neurons. Impaired performance on memory and object recognition tasks. Persistent inflammation in the brain. Effects that showed up months after a single exposure. The press called it space brain, which is glib, and the underlying finding is not. Some of the doses used were higher than a real mission would deliver, and rodents are not people, and the field argues about extrapolation constantly. What nobody argues about is the direction of the effect. Heavy nuclei damage nervous tissue in a way that does not fully heal, and there is currently no countermeasure for it. Now, the piece of this that I find genuinely perverse. You would think the answer is shielding, and for most radiation it is. Put enough mass between yourself and the source, and the problem goes away. Cosmic rays break that rule, because when a high-energy nucleus hits a heavy atom in your shield, it shatters it, and the fragments come out the other side. One incoming particle becomes a spray of dozens. Aluminium, which is what spacecraft are made of, is especially bad at this. A thin aluminium hull can deliver a higher dose behind it than no hull at all, because it converts a manageable number of primaries into a much larger number of secondary particles, including neutrons, which are very good at penetrating tissue. Shielding that is too thin is worse than nothing, and the crossover point is thicker than anybody wants to launch. The materials that work are the ones full of hydrogen. Water, polyethylene, liquid hydrogen, light nuclei fragment into less dangerous debris. So a meter of water beats a meter of steel comfortably. Serious Mars mission designs bury the crew inside their own drinking water and waste, because the only economical shielding is the stuff you are bringing anyway. It is a solution with a certain grim elegance. Numbers, briefly, because they anchor everything. On the ground, you absorb somewhere around 3 millisieverts a year from natural sources. On the space station, it runs to roughly half a millisievert a day. So a 6-month stay costs about 80, equivalent to several years of ground-level exposure crammed in a half a year. The Curiosity rover measured the cruise to Mars at about 1.8 millisieverts a day. A full Mars round trip, by Curiosity's own instrument, comes to something in the region of 2/3 of a sievert. NASA's career limit for an astronaut is 600 millisieverts, chosen to hold the extra lifetime cancer risk to a few percent. One trip to Mars roughly consumes an entire career allowance, and that is inside the heliosphere, with the sun's bubble still doing most of the work for you. Out here, there is no bubble and no magnetic field and no hull. The flux is 4 times the interplanetary figure, arriving isotropically, which is the technical word for from everywhere with no preference. There is no shaded side. You cannot turn your back on it. There is no orientation of a human body that reduces the exposure, because the sky is the source and the sky is all directions. The damage register in astronauts is already measurable, and cataracts are the clearest case. Studies of astronaut cohorts have found elevated rates of lens opacity, appearing earlier and correlating with recorded radiation dose. A 2016 paper by Michael Delp and colleagues reported higher cardiovascular mortality among Apollo astronauts who flew beyond Earth's magnetic field, and the finding has been argued about ever since because the sample size is tiny. 24 people went. That is the entire data set. Machines suffer too, which is how we notice this stuff down on Earth. A single particle striking a memory chip can flip a bit, turning a 0 into a 1, and the consequences depend entirely on which bit. Satellites reboot. Spacecraft go into safe mode. Voyager has done it more than once, and diagnosing a fault from 20 billion kilometers away with a day and a half of signal delay is a special kind of engineering. In 2003, in the Belgian municipality of Schaerbeek, an electronic voting machine awarded a candidate 4,096 extra votes. That number is 2 to the 12th power, which is exactly what you get when a single bit flips in the right position. Engineers examined the machine, found no fault, and the leading explanation on record is a cosmic ray, a particle from a dead star editing an election result. Which brings up the thing I cannot quite get past about this chapter. Every second of your life on Earth, at sea level, roughly 150 cosmic ray secondaries have been passing through your body. Constantly. Since birth, you have never felt one. The only humans who have ever perceived them directly were lying in the dark in a spacecraft, and what they perceived was light that did not exist outside their own heads. Out here the rate goes up, and the perception stays the same. Flashes in a dark visual field, with no source and no sound, and no way to look at them directly. That is the only sensory contact you will have with the most energetic phenomenon in the galaxy. It announces itself as small silent lights, and then it keeps going out the other side of your skull on its way to somewhere else. And those are the typical ones. The ordinary traffic, sitting somewhere between 100 million and 10 billion electron volts, which is already more energy per particle than anything in a hospital or a reactor. The distribution has a tail, though, and the tail goes up. Far up. Further up than physics has a comfortable explanation for. On the 15th of October, 1991, a detector array in the Utah desert recorded an event so far out along that tail that the team who found it spent months checking their instruments before they would say it out loud. The number they eventually published was so absurd that the particle acquired a nickname no journal would ever have chosen, and the nickname has stuck for 35 years. The detector was called the Fly's Eye, which is a good name for what it was, a scatter of mirrors and photomultiplier tubes staring upward from Dugway, proving ground in the Utah desert, run by the University of Utah, watching for faint flashes of ultraviolet light in the night sky. It did not detect particles. It detected the atmosphere being hit by them, which glows very faintly as it is torn apart. On the night of October 15th, 1991, it caught a flash so bright that the analysis took months, because the obvious explanation was that something had broken. The number that came out of it was 3.2 times 10 to the 20th electron volts. In everyday units, that is about 51 joules carried by a single subatomic particle, almost certainly one proton. 51 joules is not a small amount of energy, and it is not a large one either. It is the energy of a baseball thrown by a decent amateur around 90 kilometers an hour, or a brick dropped from waist height, or a golf ball rolling briskly across a green. You could absorb it on your palm without much complaint. The problem is the packaging. Because a baseball contains something like 10 to the 25th atoms sharing that energy between them. This was one proton, the entire kinetic energy of a thrown ball, concentrated into a particle with a diameter of about a quadrillionth of a meter. Physicists at the time did not have a formal designation for it, so somebody in the group called it the "oh my god" particle, and the name went into the literature and never left. Set it against our best machinery. The Large Hadron Collider, a 27-kilometer ring buried under the border of France and Switzerland, consuming the electricity of a small city, accelerates protons to about 6.8 trillion electron volts. That is the pinnacle of human engineering in this domain. The Utah particle carried roughly 47 million times more energy than that. Nature did it for free, somewhere with no ring at all. Its speed is the part where language gives up. It was moving at 99.99999 51% of the speed of light. 22 nines. Race it against a photon across the entire width of the Milky Way, 100,000 light years, and the photon wins by about 14 trillionths of a second. Relativity makes that stranger still. At that velocity, the Lorentz factor is around 300 billion, which means that from the particle's own point of view, time and distance are compressed by that same factor. The galaxy it crossed was flattened to almost nothing. In its own frame of reference, that proton crossed the entire Milky Way in about 9 seconds. Now the real problem, and it is the reason this chapter exists. In 1966, 3 physicists, Kenneth Greason working independently and Georgy Zatsepin with Vadim Kuzmin, pointed out something inconvenient. A proton above roughly 5 times 10 to the 19th electron volts will collide with photons of the cosmic microwave background, the same faint 2.7-degree glow we met earlier, and lose energy in the process. To a proton moving that fast, those harmless microwave photons are blue shifted into gamma rays. Space becomes a fog. Every few tens of millions of light years, the particle loses a chunk of energy to a collision, which puts a hard ceiling on how far one can travel before dropping below the threshold. The practical limit works out at something like 160 million light years. So the Utah particle had to come from relatively nearby, cosmologically speaking, within our own supercluster, which means we should be able to look in the direction it came from and find something enormous enough to have made it. Astronomers looked. There is nothing obvious there. That has been the state of the question for 35 years. The Utah group kept watching. The fly's eye became hires. Then the telescope array, 700 square kilometers of scintillation detectors laid out across the desert with fluorescence telescopes watching over them. On May 27, 2021, they caught another one, 2.4 times 10 to the 20th electron volts, the second most energetic particle ever recorded. They published it in Science in November 2023 and named it Amaterasu, after the Japanese sun goddess. Its arrival direction is the interesting part. Trace it backward, allowing for magnetic deflection, and it points toward a region called the local void, one of the emptiest patches of the nearby universe. No active galaxy, no obvious accelerator, no candidate source of any kind. A particle carrying the energy of a thrown brick arrived from a direction where, as far as anyone can tell, there is nothing. The Pierre Auger Observatory in Argentina, 3,000 square kilometers of tanks and telescopes on the Pampa Amarilla, has been collecting these events since 2004 and has enough of them to talk about statistics. There is a broad excess in the general direction of Centaurus A, a nearby active galaxy with a supermassive black hole and enormous jets. The telescope array sees a separate hot spot up near Ursa Major. Neither is a smoking gun. Candidate accelerators do exist on paper. Jets from supermassive black holes, gamma-ray bursts, magnetars, which are neutron stars with magnetic fields a quadrillion times Earth's. Tidal disruption events, where a star is pulled apart by a black hole. Any of them could plausibly do it. Matching a specific particle to a specific object has failed every time, because the galaxy's magnetic fields bend the paths and destroy the evidence. The rate is what saves everyone. At these energies, the flux is roughly 1 particle per square kilometer per century. That is why detectors have to be the size of small countries, and why every event is an occasion. In the whole history of the field, the number of particles recorded above 10 to the 20th electron volts is measured in dozens. What one of them would do to a human body is a question with a partial answer, because there is a documented case of a person being hit by a proton beam. In July 1978, at the U-70 synchrotron in Protvino, Soviet Union, a physicist named Anatoly Bigorsky put his head into the beam line while checking a malfunctioning piece of equipment. A safety mechanism had failed. The beam was on. He reported seeing a flash brighter than 1,000 suns and felt no pain. 76 billion electron volts of protons had passed through the back of his head, exited near his nose, and delivered a dose estimated in the hundreds of thousands of rads to the tissue along the track. His face swelled beyond recognition over the following days. Doctors expected him to die. He did not. The left half of his face was permanently paralyzed. He lost hearing in one ear. He developed seizures, and he continued working as a physicist for decades afterward. Half his face aged normally, and the other half stayed strangely smooth because the nerves were gone. It is the only real datum we have on what a concentrated beam of relativistic protons does to a living human head, and it is one man's face. A single oh my God particle would be different from that in an important way. It is one proton, so the total damage along its track is microscopic, a thin line of destroyed cells through whatever it passed through. Vygotsky took an entire beam. The relevant point is the other one. A single cosmic ray of that energy carries a macroscopic amount of energy in a subatomic object, and physics has no obligation to make that comfortable for anybody. This is the pivot in your situation, and I want to state it plainly because everything up to now has framed interstellar space as an absence. It is not. It is the most energetic environment a human body has ever occupied. Higher radiation flux than any point on Earth. Particles carrying energies our best machines cannot approach. Magnetic fields spanning 100,000 light years, currently threading through your chest. The emptiness was never protection. It was the absence of anything to absorb what is coming. On Earth, you were shielded by an atmosphere that stops all of this hundreds of times over, and by a magnetic field that deflects the rest, and by a heliosphere on top of that. 3 nested walls. Every one of them is behind you now, and what they were holding back has been arriving at your body without interruption since you got here. There's a version of this that plays out in the microwave background itself. Those 2.7-degree photons that seem so harmless in an earlier chapter are, from the perspective of anything moving fast enough, a wall of gamma radiation. Whether the universe is gentle or lethal depends entirely on your velocity relative to it. The same environment, the same photons, a completely different verdict. I find that idea difficult to put down. Nothing out here is neutral. The vacuum is a superb insulator and a terrible one depending on how fast you're going. 1/10 of an atom per cubic centimeter is negligible at 17 kilometers a second and a sandblaster at half-light speed. The medium does not change. Your relationship to it does, and that relationship decides everything. It also means the galaxy is not the quiet place the photographs suggest. It is full of accelerators, running continuously, throwing matter around at energies that make our best physics look like a hobby. Somewhere out there, something is producing 50-joule protons. It has been doing it for billions of years. We cannot find it, and its output has been passing through the planet you grew up on the entire time. About 1 particle per square kilometer per century at the top energies. Your body presents about 1.5 square meters. The odds of being hit by one specifically like the Utah event are, mercifully, so small they do not merit worry. The ordinary flux is what matters, and the ordinary flux is relentless, and it does not need to be exotic to take a body apart, which is where the next few hours are going. And I will be honest that this is the part one find hardest to write. Everything so far has been about a place. From here on, it is about a person in that place, over time, and time is the ingredient we have not yet added. 15 seconds was the opening. Nothing about your body was designed for the rest of it. Because a body is a negotiation with an environment. Bone exists to resist a specific gravitational load. Blood pressure is calibrated for a specific column of fluid in a specific orientation. Muscle mass is maintained against a specific resistance. Every one of those settings was tuned by 4 billion years of evolution on one planet, and every single one of them is now wrong. And the body will notice. Quickly, within hours, the fluid in your legs starts moving upward into your chest and your face. Within days, your skeleton begins dissolving itself, and dumping the calcium into your bloodstream. Within a month, your heart has changed shape. We know all of this precisely because we have spent 60 years measuring it on people who volunteered. Bone is not scaffolding. That is the first misconception to get rid of. It is living tissue in permanent renegotiation with the loads placed on it, being dismantled by one type of cell and rebuilt by another continuously your whole life. The system takes its instructions from mechanical stress. Load a bone and it thickens. Unload it and it disappears because a body under strict energy accounting does not maintain infrastructure nobody is using. In free fall, there is no load, not reduced load, none. So the demolition crews keep working and the construction crews stand down, and the numbers are brutal. Astronauts lose bone mineral density in the hip and lower spine at 1 to 1.5% per month. A postmenopausal woman on Earth might lose 1 to 2% in a year. Orbit does it in 4 weeks and keeps going. Over a 6-month station rotation, that adds up to figures in the region of 10% in the worst affected sites, and it does not come back easily. Follow-up studies have found that a year after landing, many astronauts have not recovered their pre-flight density, and some of the loss in trabecular bone appears to be permanent, because the internal struts do not simply thin out. They are removed entirely, and there is no template left to rebuild them from. All that calcium goes into the bloodstream and has to leave somewhere, which produces a secondary problem nobody anticipated in the early programs. Kidney stones. Calcium excretion rises sharply, urine becomes supersaturated, and crystals form. A stone in orbit, hours from any hospital, is one of the flight surgeon's genuine nightmares, and it has come close to happening more than once. Muscle goes faster than bone. Without resistance, the postural muscles, the ones that spend all day on Earth quietly holding you upright, lose their purpose immediately. Studies on early missions found losses of up to 20% of mass in the calf and thigh within a week or two. The space station now mandates over 2 hours of exercise a day on a resistive device, a treadmill with a harness, and a bike purely to slow the decline. It does not stop it. Then there is the fluid, and this is the change astronauts notice first. On Earth, gravity keeps roughly 2 liters of your blood and interstitial fluid pooled in your legs and abdomen. Remove gravity, and that fluid migrates upward within hours. Faces swell, legs thin out. Crews call it puffy face bird legs, which is exactly what it looks like in the photographs. The body reads that as too much blood volume and starts dumping it. Within days, a crew member has shed 10 to 15% of their plasma. Red blood cell production drops to match. So the astronaut is now working with less blood than they landed with, and their heart, sensing lower demand, begins to change shape. A 2014 study using ultrasound found the heart becoming about 9% more spherical in orbit. It gets rounder. It weakens. The eyes are the finding that genuinely alarmed NASA, because nobody saw it coming, and it may be the hardest problem on the list. Over the past 2 decades, flight surgeons documented a cluster of changes in long-duration crew. Swelling of the optic disc, folds in the choroid at the back of the eye, flattening of the rear of the eyeball itself, and a shift in refraction that leaves people needing different glasses when they come home. They named it spaceflight-associated neuroocular syndrome, and something like 70% of long-duration astronauts show some component of it. The leading explanation is the same headward fluid shift, raising pressure inside the skull and pressing on the back of the eye for months at a time. Some crew members recover. Some have persistent changes years later. Nobody has a countermeasure. Your immune system also loses the thread. Multiple studies have found altered white cell function, blunted responses, and shifted cytokine levels in orbit. The most vivid consequence is viral reactivation. Work led by Satish Mehta at Johnson Space Center found astronauts shedding dormant viruses in saliva and urine during flight. Epstein-Barr, varicella zoster, cytomegalovirus. Infections your body suppressed decades ago. Waking up because the guard has stopped watching. Which brings us to the single best experiment in the history of space medicine. And it happened because of a coincidence of birth. Scott Kelly and Mark Kelly are identical twins. Both became astronauts. So NASA had something it almost never gets: a genetic control group of one sitting on the ground while the other went to orbit for the better part of the year. Scott launched on March 27, 2015 and came home on March 1, 2016. 340 days. Mark stayed in Arizona and submitted to the same blood draws, the same cognitive tests, the same everything. 10 research teams across the country ran the samples. The main results were published in Science in April 2019, and the paper is one of the strangest medical documents I have ever read. Telomeres are the protective caps on the ends of chromosomes, and they shorten as you age. Everyone expected Scott's to shorten faster in orbit. They lengthened substantially and consistently throughout the mission. Then, within 48 hours of landing, they collapsed, and many ended up shorter than his pre-flight baseline, with an elevated number of short telomeres still present 6 months later. Gene expression was the bigger story. More than 1,000 genes changed their activity level during the flight, in immune function, in DNA repair, in bone formation, in the way cells handle oxygen. Most snapped back after landing. Roughly 7% did not, and were still altered half a year later. The mission ended, and part of his biology stayed in orbit. There was more. Thickening of the carotid artery wall, changes in the gut microbiome that reverted on return, an increase in chromosomal inversions, which is a marker of radiation damage to DNA, and a measurable decline in cognitive performance on speed and accuracy tasks after landing, which persisted for months in a man who had been through this before and was in excellent physical condition throughout. Scott Kelly's own account of coming home is the part one remember. He described joint pain, swelling in his legs so severe that his skin felt like it was burning, nausea, exhaustion, and a rash across his back wherever he had touched a chair. He was 52. He had been weightless for 11 months. Reintroducing him to one gravity was like putting a load on a structure that had spent a year forgetting what loads were. The record for a single flight belongs to Valery Polyakov, who spent 437 days aboard Mir between January 1994 and March 1995. He had a point to prove that a human could survive the duration of a Mars transit. When the capsule opened, he refused a stretcher and walked the short distance to a waiting chair, unsteady on his own legs because he wanted it in the record that it could be done. Every one of those people had things you do not. Air, food, water, medical monitoring, exercise equipment, a 2-hour daily program designed by specialists, a magnetic field overhead, a hull around them, colleagues to talk to, and a scheduled ride home. Every number in this chapter is the best case, achieved under supervision by trained volunteers who were being actively defended against the environment. One more thing they had, and it turns out to matter enormously: a clock. The station orbits every 90 minutes, so a crew sees 16 sunrises a day, which is useless as a circadian cue, and mission planning compensates with rigid scheduled lighting and enforced sleep periods. Even so, astronauts average around 6 hours of sleep, and something like 3/4 of shuttle aircrew use prescription sleep medication. Out here, there are no sunrises at all. No day, no night, no light level that changes ever. The human circadian system runs at slightly over 24 hours and requires daily resetting by bright light. Remove that, and the internal clock free runs, drifting later and later, until sleep and wake decouple from anything and arrive in fragments at random. Studies of people in caves and bunkers have shown exactly that drift over weeks. The thing that gets me about all of this is how orderly it is. There's nothing violent about any of it. No wound, no impact, no pain that arrives at a specific moment. Just a long series of systems correctly concluding that they are no longer needed and shutting down in an efficient, well-regulated sequence. Your body is not being attacked out here. It is being made redundant. And there is no equilibrium at the end of it. That was my assumption when I started reading this literature, that a body would adapt, find a new stable configuration, and hold it. It does not. Bone continues to demineralize for as long as anyone has measured. Muscle continues to waste. Radiation damage accumulates without limit. There is no floor. The curve keeps going down for as long as you keep going. Meanwhile, the radiation from the last 2 chapters is working the whole time. Cataracts forming in the lens. Damage to the endothelial cells lining the blood vessels. Chromosomal inversions accumulating in the marrow. Neurons losing dendritic complexity in a brain with no capacity to replace them. Every one of these processes is slow, silent, and additive, and none of them has a repair mechanism that keeps pace. Which is the moment to say the obvious thing, since I've been dancing around it for 20 minutes. You're not going to experience any of this. Your 15 seconds were spent in Chapter 1. Everything since has been a description of what the environment does to a body over years, and the body it does it to would need to be supplied with air, water, food, and a hull, and would still be losing. That is worth being clear about, because it reframes the whole problem. The reason nobody is floating out here is not that we lack the courage or the funding or the engines. It is that a human being is a device calibrated to a planet, and the calibration cannot be carried along. We're not built to leave. We are built to have already arrived somewhere and stayed there. Still, imagine the version who was supplied. Air, water, calories, a hull, a working exercise machine, decades of time. Bones thinning, eyes deforming, immune system slipping, DNA accumulating errors, and every measurement recorded neatly in a log that nobody will ever read. That person is a documented, quantified, medically comprehensible case, right up until the point where the instruments stop being able to follow them. Because there is one organ in this inventory we have not touched, and it is the one that does not show up on a bone scan. Isolation research on Earth is limited to weeks in rooms with a door that opens. Nobody has ever taken a mind into permanent, total, irreversible isolation with no possibility of contact, and then asked it what happened. The literature simply stops. What we do have is fragments. Diaries from cosmonauts who spent months in a tin can and started hating the sound of their crewmate breathing. Antarctic crews going strange in the dark half of the year. Pilots at the edge of the atmosphere reporting that they had somehow become detached from the Earth. Sailors alone at sea, absolutely certain that someone else was aboard. In the mid-1950s, as jet aircraft began routinely reaching the top of the atmosphere, Air Force psychologists started collecting a strange set of reports from pilots. At extreme altitude, alone in a cockpit, with the sky going dark above and the Earth curving away below, a substantial number of them described a sudden sensation of having become detached from the planet entirely, as though the connection had been cut. Brant Clark and Ashton Graybiel published on it in 1957 and gave a name, the break-off phenomenon. Roughly a third of the pilots they surveyed had experienced it. The descriptions split neatly in two. About half found it peaceful, even euphoric, a sense of floating free of everything. The other half found it terrifying, and several reported fighting a strong urge to turn back or descend immediately. That was at 15 kilometers in a pressurized cockpit, with a radio, in daylight, an hour from a runway. Psychologists working on future Mars missions have a name for the version they expect on a long crossing, and they call it the Earth out of view phenomenon. The reasoning is simple and unpleasant. Every human being who has ever gone anywhere has been able to look back and see home. Mars crews will be the first who cannot. Nobody knows what that does because nobody has done it. The best available guesses come from analog environments, which is the polite term for the closest miserable equivalents we can arrange on Earth: submarines, Antarctic stations, isolation chambers, and long solo voyages. All of them fall short in the same way. Every one of them has an end date, and the person inside knows it. The Antarctic literature is the richest because the continent has been running an unintentional experiment every winter since the 1950s. A station goes dark in April. The last flight leaves, and a small crew is sealed in for 6 months with no possibility of rescue in a medical emergency. The pattern that emerges is consistent enough that researchers gave it a label: winter over syndrome. Insomnia, irritability that escalates into open hostility over trivia. Depressed mood, measurable declines in memory and concentration, and a specific behavior reported so often it has its own nickname: the long eye or the Antarctic stare, in which a person sits motionless for extended periods with their gaze fixed on nothing, unresponsive, unaware of how much time has passed. Part of it may be endocrine. Researchers including Lawrence Palinkas documented systematic changes in thyroid hormone levels among winter over crews, with T3 dropping in ways that correlate with the mood and cognitive symptoms. It has been called polar T3 syndrome. Whether it is cause or consequence remains argued, and either way, there is something almost consoling in it: the possibility that a mind coming apart in the dark is partly a matter of chemistry. Orbit has produced its own literature, and the most honest document in it is a diary. Valentin Lebedev spent 211 days aboard Salyut 7 in 1982 and kept a private journal that he published years later. It is not a heroic text. It is a record of a man in a small metal room slowly running out of tolerance for absolutely everything. He wrote about the smell, about the noise of the fans, about how he and Anatoly Berezovoy, a man he respected, went through periods of barely speaking to each other in a space the size of a bus, about the crushing weight of the work schedule and the resentment it produced, about watching Earth go by and being unable to explain to anyone on it what this was actually like. Valery Ryumin, another veteran of the long Salyut flights, put it more efficiently. He quoted Chekhov in his own flight log: "All the conditions necessary for murder are met if you shut 2 men in a cabin and leave them together for 2 months." Ryumin then went and did 5 months. Twice. Soviet flight medicine had a word for the general condition that emerged in those crews: asthenization, a syndrome of fatigue, irritability, emotional flattening, sleep disruption, and reduced work capacity, appearing in long-duration crews and taken seriously enough that ground controllers monitored voice recordings for early signs. Western programs were more skeptical of it as a formal diagnosis. The crews kept reporting it anyway. Now, the sense that goes first, and it is not the one anyone expects: time. In 1962, a French geologist named Michel Siffry took himself into a cave in the Alps for 2 months with no clock, no calendar, and no daylight to find out what a human being does without external time cues. He came out convinced it was August 20th. It was September 14th. He had lost 25 days. He did it again in 1972 in a cave in Texas for 205 days. His sleep and wake cycle drifted longer, then broke down completely, then reorganized itself into cycles of around 48 hours, in which he would be awake for 30-odd hours and sleep for 12 or 14 without ever noticing that anything was unusual. He wrote of severe depression, of hallucinating, and of a mouse he tried to befriend and accidentally killed. Out here, there's no dawn, no meal, no shift change, no voice on a radio, nothing that arrives on a schedule. Every Zeitgeber, which is the term for an external cue that entrains a biological clock, is gone at once. So duration becomes unmeasurable. A minute and an hour become indistinguishable, and there is no method available to tell them apart, and no reason for the distinction to persist. The solo sailors are the closest analog we have to your specific situation because they were alone by choice for months, out of contact, with nobody to check their perceptions against. Joshua Slocum, the first person to sail around the world alone, wrote about a night in 1895 when he was feverish and had to leave the helm in a gale off the Azores. He came up on deck and found a man steering his boat. A tall figure at the wheel, dressed as a foreign sailor, who told him he was the pilot of the Pinta and that he would steer through the storm. Slocum spoke to him. They had a conversation about navigation. Slocum went back to sleep, and woke to find the boat still perfectly on course, 90 miles further on, with nobody aboard. He wrote it down as it happened and never claimed to explain it. That kind of report has a name now. In 1916, Ernest Shackleton crossed South Georgia on foot with Frank Worsley and Tom Crean after one of the worst small boat journeys in history. And afterward, he wrote that during those 36 hours, it had often seemed to him that there were 4 of them, not 3. Worsley and Crean, independently, had felt the same thing and had also said nothing at the time. T.S. Eliot read Shackleton's account and put it into the wasteland in the passage about the third who walks always beside you. A century of similar reports has accumulated since. Charles Lindbergh, crossing the Atlantic alone in 1927 and severely sleep-deprived, described presences in the fuselage behind him, speaking to him, offering advice. Frank Smythe on Everest in 1933 convinced someone was climbing with him, going so far as to divide his food to share it. Reinhold Messner reported it. Divers report it. Survivors of the World Trade Center reported it. The writer John Geiger collected the cases in a book and called it the third man factor. And the striking thing across all of them is the tone. The presence is almost never hostile. It is calm, practical, and encouraging, and in several cases people credit it with keeping them alive. There is a neurological angle. In 2014, a team, led by Olaf Blanke in Switzerland, managed to induce the sensation deliberately, using a robotic setup that created a mismatch between what a blindfolded subject's hand was doing and what their back was feeling. A third of the participants reported the distinct impression that someone was standing behind them. Some were disturbed enough to ask to stop. So the presence appears to live in the brain's model of bodies in space, in the region around the temporoparietal junction, and confuse that model badly enough, and it produces a second person who is not there, which suggests the third man is not a visitor. It is your own body sense, unmoored, handed back to you as company. That is either comforting or the single worst detail in this chapter, and I genuinely cannot decide. Then there's the case that ends the argument about whether solitude is dangerous, and it happened in 1968. 9 men set out in the Golden Globe race to sail alone and nonstop around the world, the first attempt of its kind. One of them was Donald Crowhurst, a struggling electronics businessman with a mortgaged house, an untested boat, and no realistic chance of winning. His boat began failing within weeks. Rather than retire and face ruin, he stopped in the South Atlantic, sailed in circles for months, and radioed false positions home, building a fake circumnavigation in his second logbook while keeping the real one alongside it. He was alone the entire time, and the real log survives. It starts as navigation and drifts into something else. 25,000 words of philosophy in the final weeks, about mathematics and God and the nature of the mind, about a cosmic being escaping the physical body through pure thought, growing more urgent and less legible as the pages go on. The last entries are timed to the minute. The final line is about it being finished. His boat was found empty on July 10th, 1969, sails set, everything tidy, the logbooks on the chart table. He had walked off the deck somewhere in the mid-Atlantic. And the fact I have never been able to put down is that Crowhurst had a radio the entire time. He could hear the world. He was in contact with his wife, with the press, with the race organizers. He was alone anyway. Set your situation against his and see what is missing. No radio, no wife, no press, no stjåt, no end date, no arrival, no ocean, no boat, no light, no sound, no weight, no company, and no possibility of any of those things appearing. Every constraint that made Crowhurst's isolation survivable for 8 months, you do not have. So the presence would come, eventually. That is the honest prediction from everything in the literature. Someone floating just outside your field of view, patient and calm and not there, and you would know exactly what it was, and it would not matter because there is no second opinion available anywhere within 4 light years. And a suspicion you cannot check is functionally the same thing as a fact. The other thing that would go is any sense of movement, and that one is a straightforward perceptual failure. Without reference points, your brain cannot detect velocity. Your inner ear cannot detect constant motion, only acceleration. So you would be certain you were hanging still in the dark, and you would be wrong by an enormous margin, because the actual number is one of the most absurd figures in this entire story. Nothing in your inner ear can detect constant velocity. That is worth stating first, because it explains why the rest of this chapter feels like a lie. Your vestibular system measures acceleration, changes in motion, not motion itself. Cruise at 900 kilometers an hour in an airliner, and you can pour a drink. So when I tell you what your current speed is, understand that your body has no instrument capable of contradicting me or confirming me. Start with the numbers you already own. Standing at the equator on Earth, you are being carried east at about 1,670 kilometers per hour by the planet's rotation. Faster than a rifle bullet. You have never felt it, not once, and neither has anybody else, and it took our species most of its history to accept that it was even happening. Add the orbit. Earth travels around the Sun at 29.8 kilometers per second, which is 107,000 kilometers an hour. In the time it takes to read this sentence, you covered a few hundred kilometers of that path. Both of those motions were happening simultaneously, and neither produced any sensation whatsoever because the entire system, planet, atmosphere, ocean, and you was moving together. Now, the one that matters out here. The Sun is in orbit around the center of the Milky Way at a distance of roughly 26,000 light years, moving at about 230 kilometers per second. That is 828,000 kilometers an hour. You inherited every bit of that velocity, and with nothing to slow you down, you have it still. 828,000 kilometers an hour is difficult to hold in the head, so scale it. You are covering the distance from London to New York roughly every 25 seconds. You crossed the diameter of the Earth about 6 times while I said that. And your sense of it, sitting there in the dark, is of hanging perfectly motionless in a static field of stars. One lap of that orbit takes somewhere between 225 and 250 million years. Astronomers call it a galactic year, and the Sun has completed about 20 of them since it formed. The last time the solar system occupied this approximate stretch of the galaxy, the Triassic period was underway. The first dinosaurs were appearing. The continents were still assembled into one mass. One galactic year is roughly the lifespan of a geological era. Everything from the first dinosaurs to now fits inside a single orbit, and the Sun has another 20 or so orbits left before it starts dying. If you were somehow to persist out here in one piece, you would complete a lap. You would arrive back in this neighborhood without a body, without a thought, and without anything left to register that you had made a full circuit. The velocities keep stacking. On top of its galactic orbit, the Sun is moving at about 20 kilometers per second relative to the average of the stars around it, heading toward a point in the sky near the constellation Hercules that astronomers call the solar apex. The whole galaxy is falling toward the local group center of mass. The local group is falling toward the Virgo cluster, and beyond that toward something called the Great Attractor. Measure it against the oldest reference frame available, the cosmic microwave background itself, and the solar system is moving at roughly 370 kilometers per second. The local group as a whole is doing something like 620. That is the closest thing to an absolute speed anyone can quote, and there is no way to stand still against it because there is nothing to stand on. So the word floating is wrong, and it has been wrong since the first sentence of this documentary. Floating implies suspension, something holding you up against something pulling down. Nothing is holding you. The correct word is falling, and you've been falling continuously since you got here, in a curve so enormous that no instrument in your body can register it as anything at all. Einstein worked this out in 1907 and called it the happiest thought of his life, which for him counted as excitement. He was sitting in a patent office in Bern and realized that a man falling from a roof feels no gravity. During the fall, his weight is gone, Everything in his pockets falls with him. There is no experiment he could perform inside that fall to detect that gravity was acting on him at all. That became the equivalence principle, and it is the foundation of general relativity. Free fall and weightlessness are the same state, which is why astronauts on the space station float. They're not beyond Earth's gravity. They are 400 kilometers up, where gravity is nearly 90% as strong as it is at the surface. They are falling constantly and moving sideways fast enough to keep missing the planet. You're doing the identical thing on a scale that makes orbit look domestic, falling around a mass of 100 billion suns from a distance of 26,000 light-years on a path that takes 250 million years to close. The sensation is nothing. That is the whole point of the equivalence principle. Gravity acting on every atom of you equally produces no feeling, no strain, no clue, and you cannot change it. I want to spend a minute on this because I think it is the most claustrophobic fact in this entire story. To change velocity, you need to throw mass in the opposite direction. That is the only mechanism in the universe. No wings, no wheels, no anything else, because there's nothing to push against except what you are carrying. You could throw a shoe, take a 1 kilogram object and hurl it at 10 meters per second, and a 70 kilogram body changes velocity by about 14 centimeters per second in the opposite direction. Keep that up for a year, and you have displaced yourself by 4.5 million meters. 4,500 kilometers. It sounds like a lot until you remember the nearest star is 40 trillion kilometers away. To move meaningfully, you would need to throw more mass than you have, faster than any human arm can manage, in a perfectly consistent direction, forever. There is no configuration of effort that produces a course change worth having. Your trajectory was fixed at the moment you arrived, and it is now a permanent property of you, like your height. Could you leave the galaxy? The answer is a clean no, and the number is interesting. The escape velocity from the Milky Way at the sun's distance is somewhere around 550 kilometers per second. You have 230. You are bound comfortably with less than half the speed you would need. So this orbit is not a phase you are passing through. It is where you now live. Some things do escape. There is a class of object called a hypervelocity star, flung out of the galactic center by close encounter with the supermassive black hole there, moving fast enough to leave permanently. In 2019, astronomers reported one designated SF5 HVS1, traveling at about 1,755 kilometers per second, tracked back to an ejection from the galactic center roughly 5 million years ago. That star is on its way out of the Milky Way and will never come back. It will spend the rest of its existence in intergalactic space, in an environment even emptier than the one you are in, with the galaxy shrinking behind it into a smudge. There is something in that image that stays with me. A sun thrown out of its own galaxy by something it passed too close to, still burning, going nowhere for the rest of time. The sun's path is not a smooth circle either. It bobs. The solar system oscillates up and down through the galactic plane, crossing the midline every 30 million years or so, rising some hundreds of light years above and below. Each crossing takes it through denser gas and dust, which means changing cosmic ray exposure and changing chances of a gravitational nudge to the Oort cloud. Some researchers have tried to line those crossings up with the fossil record. In 1984, Michael Rampino and Richard Stuthers argued for a roughly 30 million year periodicity in mass extinctions, matched to the plane crossings, with comet showers as the mechanism. The statistics have been contested for 40 years, and the case remains unproven. It remains, as an idea, extraordinary. Extinctions on a planet, timed by a wobble in a galaxy. There's a version of this that borders on the absurd, and I like it for that reason. Every single thing that has ever happened to your species happened during less than 1,000th of one galactic orbit. All of recorded history, all of it, occupies a stretch of the sun's path shorter than the width of the sun itself. We are a smear on the arc, and it is all still going on around you. The stars you're looking at are not fixed. They are in the same orbit, at slightly different speeds and slightly different inclinations. And over a few 100,000 years, the constellations will deform beyond recognition. The Big Dipper will come apart. Orion will lose its shape. Every pattern any human culture ever named is temporary, and you would live long enough out here to watch them dissolve. Some of them are coming toward us. In about 1.3 million years, a star called Gliese 710 will pass within roughly 10,000 astronomical units of the Sun, closer than the inner Oort cloud, and its gravity will stir up the comets out there in ways nobody can predict in detail. That is a scheduled event. It is on the calendar. It will happen whether anyone is here to see it or not. So the stillness you feel is the most complete illusion in your situation. You are traveling at 800,000 kilometers an hour on a 230 million year circuit, wobbling through a galactic plane, inside a supercluster falling toward an attractor nobody can see, and every part of that motion is invisible, unfeelable, and entirely beyond negotiation. It is the calmest violence in physics, which is when it occurs to you to look around properly at what else might be on this road. Because a body in free fall through the galaxy is not a unique object. Things fall out of solar systems. Things get thrown out of them. And a few of the things that do are considerably larger than a person. On October 19, 2017, a telescope on a mountain in Hawaii caught a fast-moving object in the inner solar system. And within days, the orbit came back with a number that had never been seen before. The trajectory was not a closed ellipse. It was a hyperbola. Whatever it was had come from outside, was passing through, and would never return. The object was found by a man named Robert Warwick, working with the Pan-STARRS Survey Telescope on Haleakala in Hawaii on October 19, 2017. It was small, faint, moving quickly, and initially unremarkable. Then the orbit came back. Every object in the solar system travels on a closed ellipse. This one was on a hyperbola with an eccentricity above 1, which means it was never bound to the sun at all. It had come in from the direction of Lyra, whipped around the sun at 87 kilometers per second, and was already heading back out when anyone noticed. Astronomers had been predicting objects like this for decades and had never caught one. The Hawaiian language experts consulted on the name chose Oumuamua, meaning something like a scout or a first messenger arriving from far off. It got the designation One Eye, the first interstellar object. The observing window was about 2.5 weeks, and every telescope that could looked. What came back was strange in almost every category. Its brightness varied by a factor of 10 as it tumbled, which implies a wildly elongated shape, possibly 6 to 1 or more. Estimates put it in the range of 100 to 400 meters long. No coma, no tal, no dust. Whatever it was not behaving like a comet. Then in June 2018, a team, led by Marco Micheli, published the finding that made the whole thing genuinely unresolved. Oumuamua was accelerating. Not much, but measurably more than gravity alone could account for, in a direction pointing away from the sun. Comets do that routinely, because venting gas acts as a thruster. Oumuamua showed no visible venting of anything. The explanations came in fast, and none of them has won. A fragment of nitrogen ice chipped off a Pluto-like body somewhere else. A hydrogen iceberg, which would vent something invisible. A cloud of frozen hydrogen trapped in amorphous water ice, released as it warmed, which is currently the leading candidate. An ultra-low-density fractal aggregate, so fluffy that sunlight itself could push it. And one more from Avi Loeb at Harvard, who argued in print that the acceleration was consistent with radiation pressure on a thin artificial sail, and that we should take seriously the possibility that it was manufactured. Most of the field disagreed, some of it sharply. What nobody can honestly claim is that the question was settled because the object left and it is not coming back, and there is nothing else to measure. The second one was easier. On August 30th, 2019, an amateur astronomer in Crimea named Gennady Borisov, using a telescope he had built himself with a 65-centimeter mirror, found a fuzzy moving object. It turned out to be unambiguously interstellar and unambiguously a comet, with a coma and a tail and a healthy supply of volatiles. It got the name 2I/Borisov, and one man in a shed beat every professional survey on Earth to it. Its chemistry was the interesting part. Observations with ALMA found an unusually high abundance of carbon monoxide, higher than almost any comet from our own system, which suggests it formed a long way out from a colder star than the Sun. A sample of the deep freeze around somebody else's home, delivered through a neighborhood at 32 kilometers per second, and analyzed while it passed. The third arrived in July 2025, picked up by the Atlas survey in Chile and designated 3I/Atlas. Another hyperbolic orbit, another object that had spent an unimaginable amount of time crossing the galaxy before happening to pass a star with astronomers around it. Early analysis suggested it may be very old indeed, older than the solar system, ejected from a star that formed in a different era of the Milky Way entirely. 3 objects in 8 years, after decades of none. That tells you something important, and it is not that we got lucky. It is that surveys finally got good enough to catch them, which means the traffic was always there. Population estimates from the discovery rate are staggering. Something like 10,000 Oumuamua-sized interstellar objects may be inside the orbit of Neptune at any given moment, passing through unobserved. Where do they come from? Mostly from the same process that made the Oort cloud running in reverse. Young planetary systems are chaotic, and a large planet migrating inward flings smaller bodies outward, some of them past escape velocity. Every star that ever formed a planetary system probably threw away a substantial fraction of its own building material. The galaxy is littered with the discards. The Sun has done it too. There are chunks of the early solar system, rock and ice that formed alongside Earth, currently drifting between the stars, ejected billions of years ago by Jupiter. They are indistinguishable from the objects arriving here, and they left before there was anything on this planet more complicated than bacteria. Our system has been exporting debris for longer than it has had continents. Now scale it up, because the same process works on planets. A system with several giant worlds is a gravitational demolition derby for its first 100 million years, and the loser gets thrown out. There is no particular limit on the size of what can be ejected. Whole planets, fully formed with atmospheres and moons and weather, can be flung out of their systems permanently. We have found them, and finding them is genuinely difficult, since an object with no star is dark and cold and radiates almost nothing. The technique is gravitational microlensing, waiting for the unseen object to pass exactly in front of a distant background star and briefly bend its light. Surveys like OGLE and MOA have been watching millions of stars for exactly that flicker for decades, and they keep finding them. The population estimates have swung around a lot and remain uncertain, but every serious count runs into the billions across the galaxy, and some models suggest free floating planets outnumber stars. The Nancy Grace Roman Space Telescope was designed with this in mind and is expected to find hundreds of them, which means the galaxy has a dark population, roughly comparable in number to its bright one, that we could barely detect until this century. In 2023, JWST turned its infrared eye on the Orion Nebula and found something almost comical. Roughly 540 objects of planetary mass, drifting free with no star to call their own, and about 40 of them were in pairs. 2 Jupiter mass objects orbiting each other in open space, with no sun anywhere in the arrangement. The team nicknamed them jumbos, and nobody has a good theory for how they form. Picture one of those worlds properly. A planet the size of Jupiter or Earth in permanent night. No day, no seasons, no sunrise, ever for the entire lifetime of the object. Its surface temperature governed only by the heat leaking out of its own interior from radioactive decay and leftover formation energy, radiating slowly away into a 2.7-degree sky. And here is the twist that keeps planetary scientists interested. In 1999, David Stevenson pointed out that an ejected Earth-sized planet with a thick hydrogen atmosphere could retain enough internal heat to keep liquid water at the surface, potentially for billions of years. A dark ocean, under a black sky, warmed from below, on a world falling through interstellar space with no sun at all. Nobody can rule it out. Then there are the failed stars, brown dwarfs, objects between roughly 13 and 80 times the mass of Jupiter, heavy enough to glow faintly from their own gravitational contraction and too light to ever ignite hydrogen fusion properly. They're the galaxy's most common category of near-miss, almost a star permanently. They cool for the rest of time. The nearest interesting one is a genuinely humbling object. In 2014, Kevin Luhman, working through WISE infrared survey data, identified something at just 7.2 light-years away, making it one of the closest systems to the Sun. It is called WISE 0855, and its temperature is around 250 Kelvin, roughly 23 degrees below freezing. It may have water clouds. The fourth nearest system to our own is a lump of cold gas about the temperature of a winter night in Norway, and nobody on Earth knew it existed until 2014. That is how thoroughly the dark hides things. We have cataloged distant quasars from the early universe with more confidence than we have cataloged our own street, which raises the worst category, and it took until recently to confirm one. Black holes formed from collapsed massive stars are not all in binary systems, where we can spot them by their effect on a companion. Most should be alone, drifting, invisible, since a black hole with nothing to eat emits nothing at all. Millions of them should be scattered through the galaxy. In 2022, a team, led by Kailash Sahu, reported the first solid detection of one, found by microlensing with Hubble, an object of roughly 7 solar masses, about 5,000 light-years away, with no companion and no light. It had been sitting there since some star died, bending the light of anything that passed behind it, and it took decades of dedicated observation to catch it doing so. So take the full inventory of your company out here. Interstellar rocks older than the solar system, comets from other people's deep freezes, rogue planets in permanent night, possibly with oceans, pairs of Jupiter-mass objects orbiting each other in the dark, brown dwarfs cooling toward the background temperature, and black holes unlit, drifting doing nothing at all. It should be comforting, and I have thought about why it is not. Every single one of those objects is in exactly your situation. Unattached, unlit, falling around the galactic center on an orbit it did not choose and cannot alter. The galaxy is full of things that got thrown away by whatever made them. You are not unusual out here. You are typical. That may be the actual insult. And the odds of encountering any of them are effectively nil, which we established 2 chapters ago. They are out there, in numbers that beggar description, and the space between them is so vast that you could drift for the age of the universe and never come within a light-year of one. Populated and unreachable at the same time. That is the specific texture of this place. Which leaves one question, and it is the one this whole documentary has been walking toward. Among all of that traffic, among the billions of rogue worlds, and the 400 billion stars, and the however many planets in habitable orbits, in a galaxy that has been running for 13 billion years, has anything out here ever tried to make itself known? We have been listening seriously with real hardware since 1960. 66 years of systematic searching across millions of stars and billions of radio channels. And the record of what we have received in all that time comes down to a single 72-second event in the summer of 1977 that nobody has ever been able to explain or repeat. The question was asked over lunch in the summer of 1950 at Los Alamos, and it was almost an interruption. Enrico Fermi was walking to the canteen with Edward Teller, Emil Konopinski, and Herbert York, and they had been joking about a cartoon in the New Yorker that blamed flying saucers for stolen garbage cans. The conversation moved on to other things. Then Fermi, out of nowhere, in the middle of the meal, said, "Where is everybody?" Everyone at the table knew immediately what he meant, which is the part one find remarkable. He had run the numbers in his head between the door and his chair. Old galaxy, many stars, ordinary physics, plenty of time. The conclusion should be a universe that is obviously, visibly inhabited. The conclusion available out of the window was a sky with nothing in it. 10 years later, a young radio astronomer named Frank Drake pointed an 85-foot dish at Green Bank, West Virginia, toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened to 1420 megahertz. He called it Project Ozma. It ran for a couple of hundred hours over several months in 1960, and it was the first deliberate search for a signal from another civilization in human history. He got hit almost immediately. A strong, regular, unmistakably artificial signal that had the whole team briefly convinced. It was a passing aircraft or classified military radar, depending on which account you read, and it was terrestrial. Drake described the sensation of it. That moment of certainty followed by the deflation, and every SETI researcher since has had a version of the same afternoon. In November 1961, Drake convened a small meeting at Green Bank to work out how to think about the problem properly, and to organize the agenda, he wrote an equation on the board. Number of stars, fraction with planets, fraction habitable, fraction where life starts, fraction where it becomes intelligent, fraction that transmits, and how long a transmitting civilization lasts. Multiply them together, and you get the number of detectable civilizations in the galaxy. The equation is often mocked for having terms nobody can measure, and the mockery misses the point of it. Drake did not intend a calculator. He intended a list of the things you have to be ignorant about, laid out in order so that people arguing about aliens would at least be arguing about the same 7 quantities. 65 years later, we have narrowed the first 3 considerably and the last 4 not at all. The first 3 are the encouraging ones. Kepler and its successors have confirmed that planets are ordinary, that most stars have them, and that rocky worlds and temperate orbits are common. Current estimates put the number of potentially habitable planets in the Milky Way in the billions. Every discovery in exoplanet science since 1995 has pushed the front of the equation in the direction of a crowded galaxy. And then there is the observational record, which is where we get to the 15th of August, 1977. Ohio State University operated a radio telescope called the Big Ear, a flat metal field with 2 reflectors, no moving parts, that let the sky drift across its beam as the Earth turned. It was searching for narrowband signals near the hydrogen line. It printed its output on continuous computer paper, which a volunteer went through by hand days later. The volunteer was Jerry Emmon. Going through the printout, he came to a sequence in one channel reading 6 EQUJ5, which in the telescope's alphanumeric intensity coding meant a signal rising to roughly 30 times the background noise and then falling away again. Narrowband, unmodulated, exactly at the frequency theorists had predicted anyone would use. He circled it in red pen and wrote one word in the margin. Wow. The signal lasted 72 seconds, which is precisely how long any fixed point in the sky took to cross the Big Ear's beam. That detail matters enormously, because it means the source behaved exactly like something out there rather than something nearby. It did not drift in frequency the way a terrestrial transmitter would. It came from the direction of Sagittarius, and it has never been detected again. Not for lack of trying. The Big Ear itself had a second feed horn that should have caught the same source minutes later and did not. Follow-up searches with far more sensitive instruments have covered that patch of sky repeatedly across 5 decades. Nothing. Explanations have included a passing satellite, an aircraft, military transmission, and in 2017 a proposal involving a pair of comets, which the SETI community largely rejected. The Big Ear was demolished in 1998. The land was wanted for an expansion of an adjacent golf course. The instrument that recorded the single most interesting 72 seconds in the history of the search for other mines was knocked down to make room for more fairway, and I have never been able to decide whether that is funny or unbearable. Everything else in the record is either terrestrial or natural. The most instructive case came in 1967, when Jocelyn Bell Burnell in Cambridge found a source pulsing with metronomic regularity every 1.33 seconds. The team joked about it, labeled the chart LGM1 for little green men, and took the possibility seriously enough to worry. It was a rotating neutron star. She had discovered pulsars. The pattern repeats. In 2015, the Parkes telescope in Australia spent 17 years detecting strange signals called peritons before somebody worked out that they occurred when staff opened the kitchen microwave before its cycle finished. In 2020, Breakthrough Listen flagged a candidate from Proxima Centauri, designated BLC-1, which held up for months of analysis and then turned out to be interference from human equipment. The searching has been serious and it has been sustained. The Ohio survey ran for over 20 years. Project Phoenix examined 800 nearby stars through the 1990s. The Allen Telescope Array came online in 2007. Breakthrough Listen launched in 2015 with $100 million from Yuri Milner and time on Green Bank, Parkes, and Automated Planet Finder, generating petabytes of data across billions of frequency channels. Total confirmed extraterrestrial signals detected in 66 years of listening. 0. That is the empirical result, and it deserves to be stated without softening. Not one ambiguous but credible repeat. Not one signal that survived scrutiny. A sky covered with hundreds of billions of stars, examined with increasingly excellent instruments for 2/3 of a century, and it is quiet. Radio is only one channel, and here is the one that genuinely disturbs me. In 2015, Jason Wright and colleagues at Penn State published a survey called Glimpsing Heat from Alien Technologies. The logic is simple. Any civilization using enormous amounts of energy has to radiate waste heat in the mid-infrared, and that heat is detectable across cosmic distances. They examined WISE survey data for about 100,000 galaxies. Not 100,000 stars. 100,000 galaxies, each containing 100 billion stars or more. They were looking for any galaxy where a significant fraction of the starlight had been captured and re-radiated as heat, which is what a civilization operating at galactic scale would inevitably look like. They found none. 10 to the 16 stars checked. Nothing anywhere has industrialized its own galaxy. Which brings up the argument that makes the silence a genuine problem rather than a curiosity, and it belongs to Michael Hart in 1975 and Frank Tipler in 1980. Suppose a civilization builds probes that can travel between stars at even 1% of light speed, and suppose those probes can build copies of themselves on arrival. Crossing the galaxy takes 10 million years. Filling it takes a few tens of millions more. The galaxy is 13 billion years old. 10 million years is less than 1,000th of that, which means that if a single technological species had emerged anywhere in the Milky Way at any point in the last few billion years and done the obvious thing, its machinery would already be in this solar system. It would have been here before the dinosaurs. The timing argument is not close. It is overwhelming. So something prevents it, and in 1998, the economist Robin Hanson gave that something a name. The Great Filter. Somewhere in the chain from dead chemistry to galaxy-spanning civilization, there's a step so improbable or so lethal that almost nothing gets past it. The filter definitely exists because the sky is empty. The only question is where it sits, and that question has a sharp edge. If the filter is behind us, we are extraordinary. Maybe the origin of life is a fluke, or the jump from simple cells to complex ones, which on Earth happened exactly once in 4 billion years. Peter Ward and Donald Brownlee argued in 2000 that the conditions for complex life require an absurd stack of coincidences, from a stabilizing large moon to plate tectonics to a gas giant in the right orbit. If they are right, we got lucky and the galaxy is ours. If the filter is ahead of us, we are food for it. Every civilization that got this far hit something and hit it reliably and nothing that reaches our stage survives the next step. In that reading, every empty exoplanet we discover is bad news, because it moves the filter later in the sequence and closer to where we are standing. Finding a fossil on Mars would be, in Nick Bostrom's phrasing, the worst news imaginable. And then there is the explanation I like least, because I cannot find a flaw in it. In 1983, David Brin published a paper called The Great Silence, in which he laid out the possibility that the quiet is deliberate, that the reason nobody transmits is that transmitting is understood everywhere to be a catastrophic mistake. Loudest turned it into the version most people know. 2 axioms. Survival is the first need of any civilization, and matter is finite while ambition is not. Add the problem that you cannot know a stranger's intentions and cannot afford to guess wrong across light years of delay, and the rational move for everybody is to stay silent and eliminate anything that is not. He called it the dark forest. Every civilization is a hunter moving carefully through the trees, and the moment one of them strikes a match, the others learn where it is. The chilling part of the argument is that it does not require anyone to be malicious. It only requires everyone to be cautious and to have no way to verify anything and to know that the other side is reasoning identically. Humans have struck several matches. The Arecibo message in 1974, written by Drake and Sagan, 1,679 bits fired at the globular cluster M13, 25,000 light-years away. The cosmic call transmissions from Evpatoria in 1999 and 2003. A message from Earth in 2008, which was assembled partly from social network submissions and aimed at a planet 20 light-years out. Brin has argued for decades that we should stop doing that until we have talked about it properly. Stephen Hawking said something similar and got mocked for it. The counter-argument, which Sagan made, is that we have been leaking radio and radar for a century and the horse has left the stable. Both positions are defensible. What is remarkable is that we have never had the conversation as a species. A few dozen people made the call. Sit with the full picture from where you are floating. 200 billion stars in this galaxy. Billions of temperate planets. 13 billion years elapsed. 66 years of listening, 100,000 galaxies checked for waste heat, and a single unrepeated 72-second event from 1977 whose instrument was bulldozed for a golf course. That is the entire evidential record of company in the universe. And the silence out here is not the same as the silence in Chapter 8. That one was acoustic, a matter of physics, and it had an explanation you could write on a napkin. This one has no explanation at all. Something is keeping the galaxy quiet, and we do not know what it is, and every candidate answer is worse than the question. There is one more possibility, and it requires no filter, no predator, and no catastrophe. It is the simplest of all of them. Perhaps nobody is transmitting because almost nobody has started yet. Perhaps we are not late to an empty party. Perhaps we are absurdly, uncomfortably early, arriving in the first thin morning of a universe that will run for a very long time. It is the kindest answer available, and it comes with a price nobody mentions. Because if this is the early universe, then everything you can see in the sky right now is at its peak. The stars are as numerous as they will ever be. The light is as plentiful as it will ever be. From here, the story of the universe is a story of subtraction, and you are in the best seat for watching it begin. The universe was better at making stars when it was younger, and we can measure by how much. By surveying galaxies at different distances, which is the same thing as surveying them at different ages, astronomers have reconstructed the cosmic star formation history in detail. It rose steeply, peaked around 10 billion years ago, and has been declining ever since. The current rate is roughly 1/30th of what it was at the peak. Our own galaxy is a fair example. The Milky Way currently converts something like 1 or 2 solar masses of gas into new stars per year. In its youth, that figure was many times higher. The gas that has not already been used is either locked up in stellar corpses or has been blown out of the disk entirely. and there is no mechanism for getting it back. By most estimates, the universe has already produced the large majority of the stars it will ever produce. That is a sentence worth reading twice. The stellar era is not building toward anything. It peaked before the Earth existed, and everything since has been a long tale. You're sitting in the skies late afternoon, and it looks like noon because there is nothing to compare it against. Start the accounting close to home, because home has the nearest deadline. The sun is getting brighter, slowly but relentlessly, as helium accumulates in its core and the core contracts and heats. Its luminosity climbs by roughly 1% every 110 million years. It has already brightened by about 30% since the Earth formed. Push that forward and you get a date for the end of the biosphere, and it arrives long before the sun does anything dramatic. Somewhere between 1 and 1.5 billion years from now, the increase in solar output tips Earth into a moist greenhouse. Water vapor floods the upper atmosphere, gets broken apart by ultraviolet light, and the hydrogen escapes to space. The oceans do not evaporate quickly. They leak away. Complex life probably goes earlier than that. Falling carbon dioxide levels, driven by the same warming through accelerated rock weathering, may start photosynthesis within 500 to 600 million years. So the plants go, and then the animals and the last inhabitants of Earth are likely to be the same heat-tolerant microbes that were here at the beginning, holding on in deep rock while the surface turns to stone and vapor. Life on Earth is roughly 3.8 billion years old, and has perhaps a billion years left, which means if you want the uncomfortable framing that the biosphere is about 80% through its run. We did not arrive early in the story of this planet. We arrived in its final act, and we arrived by luck rather than by any principle. The sun itself carries on for another 4 billion years after that, quietly, with nothing left on the surface below to notice. Then the hydrogen in the core runs out. The core contracts, the outer layers expand, and the star begins the long swelling that ends the solar system as an arrangement of objects. At around 7.5 billion years from now, the sun becomes a red giant, hundreds of times its current diameter, reaching out to roughly the orbit of Earth. Mercury and Venus are certainly consumed. Earth's fate depends on a fine balance between the expanding surface and the outward migration caused by the sun losing mass, and the modeling has gone back and forth for years. The most likely outcome is that Earth is swallowed. It is not in there. The sun burns helium, contracts, expands again on the asymptotic giant branch, and then sheds its entire outer envelope in a series of pulses, throwing roughly half its mass into space as a slowly expanding shell. For 20 or 30,000 years, that shell glows as a planetary nebula, one of the most beautiful objects in astronomy, and then it disperses into the interstellar medium. What is left is a white dwarf, about half the sun's mass compressed into a sphere roughly the size of Earth, so dense that a teaspoon of it would weigh several tons. No fusión, no energy source of any kind, just a hot cinder, radiating away leftover heat into a cold sky, cooling for an amount of time that makes the current age of the universe look like a warm-up. The other thing scheduled for that era is a collision. Andromeda is currently closing on the Milky Way at about 110 kilometers per second, and in roughly 4.5 billion years, the two galaxies begin to merge. Astronomers have simulated it repeatedly. The disks are destroyed, the spiral arms are torn out, and what forms over the following billion years is a single large elliptical galaxy with no structure left to speak of. Almost no stars will hit each other, as we covered. What the merger does is stir up the remaining gas, trigger one final burst of star formation, and then exhaust the supply. Galaxy mergers are the last big meal in a galaxy's life. After that, the new elliptical settles down into a slow, reddening decline, and every large galaxy in the universe is heading for the same condition. The stars that last are the small ones, which feels backwards until you see the mechanism. A red dwarf has a fraction of the sun's mass, so it has less fuel, but it burns that fuel with absurd stinginess, and it convects its entire interior, so it eventually uses nearly all of it. A star with a tenth of the sun's mass can shine for something like 10 trillion years. Proxima Centauri, the faint red thing next door, will still be burning when the sun has been a cold cinder for 4 trillion years. Roughly 3/4 of the stars in this galaxy are red dwarfs. They are the ones that inherit the universe. And the universe they inherit will be dim, red, and slow, lit by stars that put out a fraction of a percent of the sun's output. The final star formation event is a real, calculable moment. As the gas runs out and no more clouds can collapse, the galaxies stop producing. The last new star probably ignites somewhere between 1 and 100 trillion years from now. Fred Adams and Gregory Laughlin worked the timeline out in detail in the 1990s and called this whole bright period the Stelliferous Era, meaning the age of stars. We are near its beginning. Then it goes out, one by one, in no particular order, over trillions of years. Every star in the sky exhausts its fuel and stops. The bright ones went first long ago. The sun-like ones follow. The red dwarfs hold on for 10 trillion years, and then they go too, and the sky you are looking at right now empties, point by point, until nothing in it is producing light. Astronomers call the aftermath the degenerate era, and it runs from about 100 trillion years to something like 10 to the 40th. The universe is populated by white dwarfs cooling toward absolute zero, neutron stars doing the same, brown dwarfs that never lit at all, rogue planets, and black holes. Everything is dark. Everything is still moving. Nothing is producing energy. There is one flicker left in that era, and it is the loneliest fact I know. Occasionally, across unimaginable spans of time, 2 brown dwarfs will collide. Combine their masses, and you can cross the threshold for hydrogen fusion, and a new star ignites out of 2 failures. In a galaxy the size of ours, this might happen once every 10 to the 15 years. Roughly 100 of them burning at any moment in a completely dark universe. 100 stars in a galaxy that used to hold 400 billion, lighting up by accident, burning for a few billion years and going out. That is the universe's last attempt at making anything. It will keep making them at that rate for an amount of time so long that the numbers stop communicating anything, and then it will run out of brown dwarfs too. Meanwhile, something else is happening, and it is the part of modern cosmology I find hardest to accept emotionally, even though the evidence is excellent. The expansion of the universe is accelerating. It was discovered in 1998 by 2 competing teams studying distant supernovae, and it won a Nobel Prize in 2011, and nobody knows what is driving it beyond the placeholder name dark energy. Accelerating expansion means distant galaxies are receding faster over time, and eventually faster than light can close the gap. They cross a horizon and become permanently unreachable and then permanently invisible. This is already happening. Objects beyond roughly 16 billion light years are already receding faster than their light can travel toward us. We can see them because the light is old. We can never reach them or affect them in any way. In about 150 billion years, every galaxy outside our own gravitationally bound local group will have crossed that horizon. In a couple of trillion years, their light will be redshifted and dimmed beyond any conceivable detection. The sky of that era contains exactly one galaxy, the merged remnant of the Milky Way and Andromeda. Everything else is gone, and not gone as in destroyed, gone as in unobservable. Lawrence Krauss and Robert Scherer wrote a paper about this in 2007 that has stayed with me for years. Astronomers in that era, if there are any, would look out and see one galaxy in a static void. No redshift to measure, because there would be nothing left to measure it against. No cosmic microwave background stretched beyond detection. No evidence of the Big Bang whatsoever. They would conclude, entirely reasonably, from all available evidence, that they lived in a single eternal island of stars in an unchanging emptiness. They would be wrong. everything they needed to know would have already left the observable universe. The truth about the cosmos is available for a window, and the window is closing, and we happen to be inside it. That reframes what you are looking at from where you float. The sky above you contains the light of 200 billion stars in this galaxy and the smudges of galaxies beyond it. And that view is temporary. Not on a human scale, but temporary in the only sense that matters, which is that it is strictly better now than it will ever be again. Every year, there is very slightly less to see. There's a phrase for this in the literature, and it is unusually blunt for a scientific term: the heat death. The gradual approach to a state where all energy is evenly distributed, all temperature differences have equalized, and nothing further can happen anywhere, because every process that has ever occurred required a difference between one place and another. Entropy is the accountant here, and it never posts a credit. Every star that burns, every collision, every thought anybody has ever had has increased the total disorder of a universe and moved it closer to that flat state. Life is not exempt. A living thing maintains its internal order by exporting more disorder outward. You have spent your whole existence accelerating this. So the dimming has already begun, and it began before we existed. Peak star formation was 10 billion years ago. Peak brightness for any given galaxy is behind it. The gas is running down, the expansion is carrying the rest away, and the process has no reverse gear and no external supply. It is the most reliable prediction in physics and the least discussed. And you would see it happen. That is the specific cruelty of imagining a body that persists out here. Not a sudden ending. A sky that thins gradually over trillions of years as the points of light stop one at a time and are not replaced until the last red dwarf goes cold and the constellations are made of nothing. But the universe is not empty at that point, and this is where the story gets genuinely strange. Something survives the death of every star, keeps functioning, keeps growing, and dominates the cosmos for a span of time, next to which the entire stellar era is a brief flash at the beginning. They were there the whole time. They were simply waiting for the lights to go out. There are somewhere around 100 million stellar mass black holes in this galaxy alone, and a supermassive one at the center with 4 million times the mass of the Sun. They do not burn. They do not run out of fuel. They have no life cycle in the way a star does. And in the era after the last light, they're the only structures left with anything happening inside them. Numbers are about to stop working, so let me set up the scale first. A billion is 10 to the 9th. The age of a universe is about 10 to the 10th years. Everything from here on will be written as powers of 10, and each step up is a multiplication by 10, and by the end of this chapter we will be at 10 to the 100th. There is no way to make that feel like a duration. There is only the notation. Start with the cinders. A white dwarf has no energy source, so it simply radiates its stored heat away, cooling like a poker pulled from fire. The cooling slows as it gets colder, so the last few degrees take absurdly long. After roughly 10 to the 15th years, a quadrillion years, a white dwarf has come down to something near the temperature of the background sky, and at that point it is called a black dwarf. There are no black dwarfs yet. The universe has not existed for long enough to produce a single one. Every white dwarf in the sky right now is still glowing, still warm, still working through the first fraction of a percent of its cooling curve. The oldest one out there has barely started. That is how young this universe actually is. Now the question that decides how the rest of it unfolds. Is a proton stable? Ordinary matter is made of them. And if they last forever, then the corpses of stars persist essentially indefinitely. Several theories that unify the fundamental forces predict that protons should very occasionally decay, spontaneously, into lighter particles. Nobody has ever seen it happen. Not for lack of watching. Deep under a mountain in Japan, there is a tank called Super Kimio Candy holding 50,000 tons of ultra-pure water, lined with photomultiplier tubes, monitored continuously for decades. If a single proton in all that water decayed, they would see the flash. They have not. The experiment sets a lower bound on the proton lifetime of more than 10 to the 34th years. 10 to the 34th years is 100 trillion times the current age of the universe, and it is a floor rather than an answer. If protons do decay somewhere above that number, then every atom in every black dwarf and every rogue planet and every remaining scrap of matter eventually dissolves, and by around 10 to the 40th years the universe contains no ordinary matter at all. Consider what that means for the mummified body we left drifting back in Chapter 2. The freeze-dried, perfectly preserved, indefinitely stable object with its face intact. On this timescale, it does not erode or decay or get eaten. Its protons individually cease to exist, one at a time, over spans that dwarf everything, until the shape is not there because the matter is not there. If protons are stable, it goes differently and somehow worse. Quantum tunneling would slowly rearrange matter into its most bound configuration, which is iron. Over something like 10 to the 1500th years, every cold remnant becomes an iron sphere. That number has 1500 zeros. It is written down in serious papers by serious people, and there is no honest way to describe how long it is. Either way, the stellar corpses are on their way out, and the things that outlast them are the black holes. Which brings us to 1974 and the single most surprising theoretical result of the 20th century, produced by a 32-year-old physicist who had been told he had 2 years to live a decade earlier. Stephen Hawking showed that black holes are not perfectly black. Quantum field theory at the event horizon produces a faint thermal glow, now called Hawking radiation, which carries energy away. And energy is mass. So a black hole, given enough time and nothing to eat, loses mass, shrinks, and eventually disappears entirely. The most inescapable object in physics turns out to be slowly leaking. The rate is set by the temperature, and the temperature is inversely proportional to mass, which produces a wonderfully strange consequence. Big black holes are colder than small ones. A black hole with 10 times the sun's mass has a temperature of about 6 billionths of Kelvin. That is far colder than the 2.7 degree background it is sitting in. So it cannot start evaporating yet. It absorbs more energy from the microwave background than it emits, and it will keep gaining mass until the universe cools below its own temperature. That takes on the order of 10 to the 12th years. Every black hole in existence today is currently growing very slightly on cosmic background radiation, and none of them can begin to die until the sky itself gets colder than they are. Once that threshold passes the clock start, a 10 solar mass black hole takes roughly 10 to the 69th years to evaporate completely. Sagittarius A star, the 4 million solar mass object at the center of our galaxy, needs something like 10 to the 87th. The largest known black holes, monsters like TON 618 with tens of billions of solar masses, come in near 10 to the 100th. The way one dies is the detail that gets me. As it loses mass, it gets hotter, and as it gets hotter, it radiates faster, which makes it lose mass faster still. The process runs away. After spending 10 to the 99th years radiating almost nothing at a temperature colder than anything, the final second is an explosion, releasing energy comparable to millions of megatons of TNT in a single flash. So the last events in the history of the universe are small, brilliant, isolated detonations, scattered across an unimaginable volume, separated from each other by spans of time with no useful names. Nothing sees them. Nothing is left to see anything. The universe ends with a scatter of bright flashes going off in an empty room, and then it does not do that anymore either. After 10 to the 100th years comes what cosmologists call the Dark Era, and the accounting here is genuinely surreal. What remains is a thin gas of the particles that do not decay. Photons, neutrinos, electrons, and positrons spread across a volume that has been expanding exponentially the entire time. The density is so low that the distances between individual particles exceed the size of the present observable universe. Fred Adams and Gregory Laughlin worked out one consequence that I have never been able to shake. Occasionally, an electron and a positron would find each other and form a bound pair, a giant atom of positronium. At those densities, the orbital radius would be larger than a galaxy. Larger, in fact, than the entire visible universe is today. An atom the size of everything, with two particles in it, taking geological ages to complete one orbit. And then, over an unfathomable stretch, that pair would spiral together and annihilate into a pair of photons, which would fly off forever in an expanding void. That is a complete event from formation to annihilation in the deep future. That is what happens. That is the news of that era, and there is no era after it that has any news at all. Which is the state physicists call heat death, and the name is misleading because nothing is hot. It means maximum entropy. Energy so evenly distributed that there are no differences left anywhere. And every process in the universe, every one, from a star fusing hydrogen to a neuron firing to a cup of tea cooling, requires a difference between one place and another. Remove the differences and nothing can occur. Not nothing much. Nothing. No motion that means anything. No change. No sequence of events. And therefore no way to distinguish one moment from the next. Which means that time itself loses any operational meaning. A universe where nothing can happen is a universe in which the question of how long it has been doing that has no answer. There are alternatives on the table, and none of them are comforting. If dark energy is stronger than the standard model assumes, the expansion could tear the universe apart in a big rip, pulling galaxies, then stars, then planets, then atoms to pieces, potentially within about 22 billion years. That would be quicker. It would also happen while the stars were still burning, which makes it considerably more vivid. There's also the possibility that the vacuum we live in is not the lowest energy state available. The measured mass of the Higgs boson sits uncomfortably close to a boundary that would make our vacuum metastable, which means a bubble of true vacuum could in principle nucleate somewhere and expand at the speed of light, rewriting physics inside it. You would receive no warning, because the warning travels at the same speed as the event. The estimated timescale for that, if it happens at all, is enormously longer than the current age of the universe. So, it is not a practical worry. I mention it because of what it implies about the ground you have been standing on. The stability of physics may be a local condition with a finite lifetime, and if it ends everywhere, all at once, with no possibility of noticing. Some theorists go further and argue about Poincare recurrence, the idea that in an infinite span of time, random quantum fluctuations must eventually reassemble any configuration, including this one, including you. Others point out that fluctuations are far more likely to produce a single disembodied consciousness than a whole universe, which produces the Boltzmann brain problem, and which most physicists treat as a sign that something in the assumptions is broken. I bring that up mostly to note where the honest edge of knowledge is. Everything up to the death of the last black hole is standard physics extrapolated with reasonable confidence. Everything past, it is speculation with mathematics attached. The one thing that is not in doubt is the direction, and the direction is toward less. Less structure, less energy available, less happening forever. Which puts your situation in a particular light, and it is the light this whole documentary has been walking toward. You are floating in the emptiest place a human being can be, in the coldest environment that currently exists, in a galaxy that has stopped making stars as fast as it used to, in the early bright morning of a universe that is 10 to the 100th years of darkness ahead of it. And this is the good part. That is what I keep circling back to. Right now, at this moment, there are stars everywhere. There is a galaxy overhead with visible structure. There is a planet a few light years back covered in oceans and animals and arguments. And there's a species on it that built machines to look at all of this. This is the peak. We are living in it. The stelliferous era, the age of stars, runs from roughly 100 million years after the Big Bang to about 100 trillion years from now. Against the full 10 to the 100th year span of the black hole era, that entire bright window is a rounding error at the front. If the history of a universe were a book, everything with light in it would be the first word on the first page. We are in the first word, not near the beginning. In it, every star that has ever formed, every planet, every living thing anywhere, all of it inside a sliver at the very start of a story that continues for a length of time the notation can barely hold. That is either the most depressing fact in this documentary or the most extraordinary privilege available, and I have gone back and forth on it for weeks. Because a handful of people worked all of this out. Not aliens, not a civilization with a million-year head start. Primates on a wet rock in about 400 years, using glass lenses and mathematics, and a great deal of arguing. The proton lifetime, the black hole evaporation timescales, the star formation history, the temperature of the background sky. We're the only thing we know of that has ever bothered to find out. And in 1977, some of those people did something about it. They knew about entropy and heat death and the distances and the silence, all of it in outline. They understood exactly how empty this place is and how unlikely it is that anything would ever find what they were about to send. And they built it anyway, and they put a great deal of care into it. It is a phonograph record, gold-plated copper, 12 inches across, bolted to the side of a machine that is now the furthest human object from Earth, currently drifting through the same interstellar space you're floating in. It carries the sound of a human heartbeat, whale song, thunder, a mother speaking to her child, and a piece of music recorded by a blind street preacher in 1927. Voyager 2 left Cape Canaveral on August 20th, 1977. Voyager 1 followed on September 5th, launched second and given a faster trajectory, so it arrived first, which is why the numbering looks wrong to everybody who notices it. Bolted to the side of each spacecraft, in an aluminum case, was a phonograph record. Gold-plated copper, 12 inches across, meant to be played at 16 2/3 revolutions per minute. They included a stylus and a cartridge taped inside the case, because it seemed sensible to provide the needle along with the groove. And on the aluminum cover they etched instructions, a diagram of the record with the stylus in position, the rotation speed expressed in units derived from the hydrogen atom, and a picture of the waveform you should expect if you have set it up correctly. The cover also carries a map, and the map is the most elegant object humans have ever engraved on anything. 14 lines radiate from a central point. Each represents a pulsar, a rotating neutron star, and the binary notation along each line gives its precise spin period. Pulsars have unique, extremely stable periods that slow at known rates, so any recipient with decent astronomy can identify all 14. Triangulate from those 14, and you get the position of the sun. Compare the periods on the plate against the periods you measure, and the difference tells you how much time has elapsed since it was made. The map is a coordinate and a clock in the same drawing, readable by anyone anywhere in the galaxy, and it will still work in 100 million years. Frank Drake designed it. There is one more detail on that cover, a small patch of electroplated uranium-238, whose half-life is 4.5 billion years. Measure how much of it has decayed, and you know the age of the object directly without the pulsars. They put a radioactive clock on the lid in 1977 for a reader they had no reason to believe existed. The committee that assembled the contents was chaired by Carl Sagan and had about 6 weeks to do it. 6 weeks for a message intended to represent an entire planet for 1 billion years. Frank Drake handled the technical encoding. Timothy Ferris produced the music. John Lomberg directed the visual design. Linda Salzman Sagan collected the greetings. And Drew Yin, then in her 20s, was creative director. They encoded 115 images as analog waveforms in the outer portion of the disk. Mathematical and physical definitions first, so the reader can calibrate. Then the solar system, then chemistry, then DNA structure, then human anatomy in cross-section, then a fetus, then a woman nursing a child, then people eating, drinking, licking an ice cream cone, building a house, running a race. A supermarket aisle full of produce, a Thai craftsman, Bushman hunters, the Great Wall, the Taj Mahal, the Golden Gate Bridge, a violin with a page of sheet music in case somebody wanted to cross-reference the audio, a Titan Centaur launch, an astronaut in space, a photograph of a page from a book by Isaac Newton. Somebody in that room thought very hard about what to include. There is one gap worth mentioning. The team wanted to include a photograph of a nude man and woman for anatomical clarity, and NASA declined. The compromise was a diagram of silhouettes with a woman's reproductive system shown in outline. An agency capable of throwing a phonograph record out of the solar system could not quite bring itself to include a picture of a person without clothes. Then the greetings. 55 languages, most recorded at Cornell in a single afternoon by whoever happened to be available and could speak one. Sumerian and Hittite are in there, spoken by academics. Dead languages sent to the stars. Akkadian, ancient Greek. Nick Sagan, Carl's 6-year-old son, recorded the English one. He said hello from the children of planet Earth. After the voices come the sounds of Earth, assembled by Drew Yin, and the list reads like a poem somebody built out of a field recording archive. Volcanoes, earthquake, thunder, zen, surf, crickets and frogs, birds, a hyena, an elephant, a chimpanzee, a dog domesticated barking, footsteps and heartbeats, laughter, a quiche, a mother speaking to her infant, fire, tools, a tractor, a Saturn V launch, Morse code, and whale song, humpback whales, spliced into the greetings so that their song runs underneath the human voices, because Drew Yin reasoned that whales had been on this planet far longer than we had, and their message deserved to travel too. That decision was made by a person in her 20s in about 1977 with a deadline, and it remains one of the most graceful things anyone has done with a spacecraft. 90 minutes of music followed, and the selection is deliberately, gloriously unbalanced toward the whole planet rather than the West. Javanese court gamelan, Senegalese percussion, Aboriginal songs from Australia, a Navajo night chant, Bulgarian folk singing, Peruvian panpipes, and a Peruvian wedding song, a Georgian men's chorus, a Chinese Guqin piece called Flowing Streams, over 2,000 years old, an Azerbaijani balaban, a raga sung by Kesarbai Kirker, Mexican mariachi, 3 separate pieces by Bach and 2 by Beethoven, plus Mozart's Queen of the Night and Stravinsky's Rite of Spring, Louis Armstrong playing Melancholy Blues, and Chuck Berry, Johnny B. Good, which Sagan had to defend against committee members who thought rock and roll was adolescent. His response was that adolescence is a real condition and rock is a good expression of it. One thing they wanted and could not get was Here Comes the Sun. The Beatles themselves reportedly approved. Their record company held the rights and refused permission, which means that somewhere in a filing cabinet in London in 1977, there was a lawyer who said no to the Voyager mission. I think about that person more than is healthy. The Bulgarian song is where this story turns into something else. Drew Yin had been hunting for a particular kind of folk recording and found it. Islil Gilio Hagduten, sung by Valia Balkanska, a shepherd's song about a rebel, sung in a voice with no softness in it all. On June 1st, 1977, she called Sagan's hotel to tell him she had found it. He was away. She left a message. He called back an hour later. They talked about the song. And then, in the way these things actually happen, without either of them planning it, they told each other that they were in love, having never once discussed it before. They had been working together for months. They were engaged within days. Drew Yin later described putting the phone down and feeling like a scientist who had just confirmed a result. 2 days after that phone call, she went to Bellevue Hospital in New York and had herself wired to an electroencephalograph. For 1 hour, she lay still, monitored and meditated deliberately, on the history of Earth, on the civilizations that had risen and fallen, on the violence and the achievements, and on what it felt like to be a person who had just fallen in love. That hour of her brain activity, along with her heartbeat and her REM sleep patterns, was compressed into about a minute of audio and pressed into the record. It sounds like a burst of static. It is on both Voyager's and Interstellar space right now, and it will be there when the sun is a white dwarf. The Thoughts of a Woman in Love, in June 1977, encoded in a groove and thrown out of the solar system. She married Sagan in 1981. He died in 1996 at 62 of complications from myelodysplasia after 3 bone marrow transplants. She has spent the decades since talking about the record and about him, and the thing she keeps returning to is that the golden record is a document of a species that was capable of hoping under circumstances where hope was not justified by any evidence. Which brings us to the last track. Sagan chose it, and the choice tells you everything about how clearly he understood what he was doing. Dark was the night, cold was the ground, recorded on December 3rd, 1927 in Dallas, Texas, by a blind street preacher named Blind Willie Johnson. There are no words in it. Johnson hums, low and rough, over a slide guitar played with a pocket knife for 3 minutes. It is a wordless song about the crucifixion, and it is one of the most desolate pieces of music ever committed to a recording. Sagan's reasoning, which he wrote down, was that the song is about being alone in the dark and not knowing whether the night will end. Johnson's life supports the choice. He was blinded as a child, reportedly by lie thrown during a domestic fight. He played on street corners in Texas for coins for decades. In 1945, his house in Beaumont burned down, and he had nowhere else to go. So he slept in the wet ashes, contracted a fever, and was refused admission to a hospital. He died shortly after and was buried in an unmarked grave. Nobody knows what he looked like. There are 2 photographs that may be him and no certainty about either. He earned almost nothing from his recordings, and his voice is now the furthest traveled sound any human being has ever made, further than any music ever performed, going out into the dark at 17 kilometers per second, with no destination and no listener. The final piece on the record is the Cavatina from Beethoven's String Quartet No. 13, which Beethoven wrote at the end of his life, deaf and marked with the word beklemmt, meaning oppressed or anguished. Sagan put last, a composer who could not hear his own music, closing a message from a species to whatever might one day be able to hear it. Now the odds, which everyone involved understood perfectly. Voyager 1 is not aimed at any star. In about 40,000 years, it passes within a light and a half years of a dim object called Gliese 445, which is not close. Neither spacecraft will ever enter another solar system. The probability of the record being found by anything is not small. It is, for all practical purposes, 0. Sagan said it plainly at the time. The launching of this bottle into the cosmic ocean, he wrote, says something very hopeful about life on this planet. He was not claiming anybody would find it. He was pointing out what it meant that we had made it at all, knowing nobody would. And it will last. The record's surface, in the vacuum and cold of interstellar space, with no oxygen and no weather and essentially no erosion, should remain playable for something on the order of 1 billion years. Longer than the biosphere has left. Longer than the continents will keep their current arrangement. It is the most durable object our species has ever manufactured, and it is a record of somebody's brainwaves in a whale. President Carter's message is on there too, dated June 16, 1977, and the last line of it has stayed with me for years. He wrote that the record represents our hope, our determination, and our goodwill in a vast and awesome universe. A politician wrote that. A politician, in an election cycle, signed off on a sentence intended for readers 1 billion years away. So this is the one warm thing in 5 hours of void, and it is worth being precise about why it is warm. Everything else in this documentary is something the universe does to a body. This is the only thing in it that a group of people chose to do back. They knew the distances. They knew the silence. They knew the odds. They made the object anyway, and they made it beautiful. And both copies are out there right now, in the interstellar medium, on the same galactic orbit you are on, being brushed by the same tenth of an atom per cubic centimeter and the same cosmic rays and the same 2.7 degree sky, which is the last thing I have to tell you, and it is the reason I have spent 5 hours saying you instead of them. I have been describing your situation for 5 hours, and I have not once been describing a hypothetical. Every fact in this documentary, the temperature, the radiation, the medium, the silence, the distances, the orbit, the deep future, applies to the exact place you're sitting right now. You are floating alone in interstellar space. You have been doing it your entire life. Nobody told you because there was no useful moment to bring it up. Start with the object you're standing on, described honestly and without the usual language. It is a ball of iron and silicate rock, 12,742 kilometers across, with no propulsion of any kind. It has no engine. It has no steering. It has no pilot, no crew, no maintenance schedule, and nothing whatsoever holding it up. It is in free fall. That is the correct technical description, and it has been true since the day it formed. It is falling around the sun, endlessly, moving sideways fast enough to keep missing it at 107,000 kilometers per hour. The equivalence principle from Chapter 14 applies here identically. You feel nothing because everything around you is falling at exactly the same rate. And the sun is falling too, around the galactic center at 828,000 kilometers an hour, carrying the Earth with it on a 230 million year circuit. Add the spin of the planet, another 1,670 kilometers an hour at the equator. Every one of those velocities was in the chapter about being lost in the void, and every one of them has your address on it. The heliosphere from Chapter 4 is above you. The local interstellar cloud from Chapter 5 is what the heliosphere is currently pushing against. And the local bubble blown open by 15 supernovae is the cavity you are inside. Those are not distant structures. They're the layers of the room in order, and the innermost one is your own atmosphere. So let's talk about the atmosphere, because it is the whole difference between this chapter and Chapter 1. The total mass of Earth's air is about 5 times 10 to the 18th kilograms. The mass of the planet is about 6 times 10 to the 24th. Divide one by the other, and the atmosphere comes to roughly 1/millionth of the object it is attached to. The usual comparison is an apple, and it undersells it. If Earth were an apple, the atmosphere would be considerably thinner than the skin. Every astronaut who has photographed the limb of the planet from orbit has taken the same picture, a bright blue line, a few pixels wide, fading to black. That line is the entire supply. There is no reserve tank. It is also concentrated at the bottom, which most people do not realize. Half the mass of the atmosphere sits below 5.5 kilometers. 99% of it is below 32. Above that, there is technically air in the sense that there are molecules present, and none of it is any use to a lung. The breathable part of the planet is a film a few kilometers thick on a 12,000 kilometer sphere. Everest makes the point better than any diagram. At 8,849 meters, the pressure is about a third of sea level, and climbers call the top of it the death zone because the human body cannot acclimatize there at all. It simply deteriorates hour by hour until you leave. That is at 9 kilometers. You cannot survive unaided at 9% of the way to the edge of space. And at 19 kilometers up you reach the Armstrong limit from Chapter 1, where the pressure drops below 63 millibars and the water in a human body boils at body temperature. 19 kilometers. That is a 20-minute drive, pointed upward. The physics that opened this documentary begins about the distance from your house to the next town, straight up. Now the question nobody asks about air. What is holding it there? There is no lid, no container, no membrane, no field. The only thing keeping the atmosphere attached to this planet is gravity, and gravity is a very gentle thing. Individual molecules at the top of the atmosphere are constantly escaping, and the planet loses a small amount of hydrogen and helium to space every single day. There's a planet next door that lost the argument. Mars is about 1/10 of Earth's mass, so its grip was weaker, and it lost its global magnetic field roughly 4 billion years ago when its core cooled. NASA's MAVEN orbiter has spent over a decade measuring what happened next. The solar wind stripping the upper atmosphere away, molecule by molecule, for billions of years. What is left is 6 millibars, less than 1% of Earth's pressure, which is well below the Armstrong limit, which means the surface of Mars is a place where your saliva would boil. And it was not always like that. There are river valleys on Mars. There are deltas and lake beds and rounded pebbles that could only have been shaped by running water. It had weather. It had an ocean's worth of water. It lost all of it. The planet on the other side failed in the opposite direction. Venus is nearly Earth's twin in size and mass, and its surface pressure is 92 times ours. Its temperature 464 degrees Celsius, hot enough to melt lead, under permanent cloud, made of sulfuric acid. It probably had oceans once. A runaway greenhouse took them, and the water went to the upper atmosphere and then to space. 3 rocky planets, all formed at the same time out of the same disk, all roughly in the same region of the solar system. One is a freeze-dried desert with an atmosphere thin enough to boil blood. One is a pressurized furnace. One has robins in it. Nothing intervened to make that happen. It is a set of initial conditions and 4.5 billion years of consequences. Earth has one thing the other two lack, and it has generated 1,100 kilometers under your feet. The outer core is liquid iron, 2,000 kilometers thick, convecting as heat escapes from the inner core, and that motion generates the planet's magnetic field. A dynamo, a spinning ball of molten metal, producing the field that deflects the solar wind and keeps the atmosphere from being blown off. It is not a permanent arrangement. The inner core is solidifying, growing by about 1 millimeter a year, and when enough of the outer core freezes, the dynamo will weaken and eventually stop. That is billions of years away. Meanwhile, the field is not even stable in short term. It flips completely north for south every few 100,000 years, and the last full reversal was around 780,000 years ago. During those transitions, the field's strength drops substantially for centuries, and more radiation reaches the surface. Right now, incidentally, the dipole has weakened by something like 9% since accurate measurements began in the 1830s, and the South Atlantic anomaly, where the field is weakest, is growing. Nobody is certain what that means. Satellites passing through it already have to switch instruments off. Above that, the ozone layer, which absorbs the ultraviolet that would otherwise sterilize the surface. If you compressed all the ozone in the atmosphere down to sea level pressure, the layer would be about 3 millimeters thick. 3 millimeters of gas is the difference between a functioning biosphere and a burnt one. In the 1980s, we nearly destroyed it with aerosol propellants by accident. And the life itself is thinner than people imagine. A 2018 census led by Yinon Bar put the total biomass of Earth at around 550 gigatons of carbon. Plants are 450 of that. Bacteria is 70. All animals together come to about 2. Humans are roughly 0.06 gigatons, and every wild mammal on the planet combined comes to about 0.007. The vertical extent is just as tight. Life reaches maybe 5 kilometers into the crust, where microbes live in rock, and a few kilometers into the air as drifting spores. Call it a shell 20 kilometers thick on a body 12,700 kilometers in diameter. Expressed as a fraction, the entire biosphere occupies about 1,000th of the planet's radius. It is a stain on the surface. None of this is managed. That is the part one want to be careful about, because it is easy to slide into cosmic sentiment and miss the actual point. There is no thermostat. There is no oversight. The temperature of this planet is the output of a chemical and radiative balance that has swung wildly across geological time, into total glaciation and into hothouse states, entirely without reference to whatever was living here. And it takes hits. 66 million years ago, an object somewhere between 10 and 15 kilometers across arrived in what is now the Yucatan, and roughly 3/4 of species on Earth ceased to exist. There was no warning system and no possible response. It happened, and the survivors inherited the planet, and one branch of them eventually got around to building telescopes and noticing that it could happen again. We have exactly one demonstrated countermeasure, and it is 4 years old. On September 26, 2022, a NASA spacecraft called DART deliberately crashed into a small asteroid named Dimorphos at over 20,000 kilometers per hour and changed its orbital period by about 32 minutes. It worked. That is the entire planetary defense capability of Earth. One successful experiment on one rock that was never a threat. So run the inventory one more time, using the chapters we have already done. You are in free fall at 800,000 kilometers an hour, inside a bubble blown by a star with about 1 billion habitable years left on it, in a cavity carved by exploding suns, holding 1/1,000,000th of your planet's mass as breathable gas, shielded by a magnetic field made of molten iron that periodically switches off. The cosmic rays from Chapter 10 are hitting you right now, about 150 secondary particles through your body every second, all day, all your life. The 2.7-degree sky from Chapter 2 is directly overhead with 100 kilometers of gas in front of it. The great silence from Chapter 16 applies to your window as much as to any point in the galaxy. Nothing about your situation is different in kind, only in comfort. Here is where I land on it. After all of this, the astronauts who looked back at Earth from the moon consistently reported the same thing. And the strange part is that they were not describing new information. Everything they realized up there was already known down here. Bill Anders said afterward that they went all that way to explore the moon, and the most important thing they discovered was the Earth. The overview effect does not require a rocket. It requires holding two facts at once: that this planet is a small, unpowered object falling through an environment that would kill you in 15 seconds, and that it is nonetheless covered in oceans and forests and animals and people who write music. Both things are true simultaneously and permanently, and it is difficult to keep them both in your head for more than about a minute. There's a version of this that I find genuinely consoling, and I want to end on it because 5 hours of void has earned one honest kindness. You are floating alone in interstellar space, and so is everyone else. 8 billion people on the same rock, in the same free fall, holding the same thin envelope of gas around themselves, moving at the same absurd speed in the same direction. Alone, in company, at 800,000 kilometers an hour. And we sent a record out. That is the thing I keep coming back to. A species that had only just worked out how far away everything is, and how quiet it is, and how it all ends, took the time in 1977 to press whale song and a Bulgarian shepherd's melody and one woman's brainwaves into gold and throw it in the direction of nothing. It is still going. It is out past everything in the dark with our names on it. The void never had to come and find you. There is nothing to escape from and nowhere safe to leave. You were born in interstellar space, on a small falling object with a film of air on it, and you have spent your entire life there, and you will finish it there, and the only difference between your circumstances and the first 15 seconds of this story is 100 kilometers of gas that gravity happens to be holding down.